since the last time this community was able to gather in person. So very exciting for me. I hope everyone here in the room is looking forward to a great week of talks, great week of interactions, chance to learn and
with the mic, but I want to see if this is going to cause.
So 7 years ago, our forefathers brought forth upon this nation,
That one is on.
upon this continent, a new nation.
That's the problem. This one is also on.
Anybody else know this? Conceived in liberty. All right. Friends, Romans, countrymen, lend me your ears. I come to bury Caesar, not to praise him.
You're really you've memorized a lot of that. That's great.
The evil men do lives after them. The good is often turned with their bones.
Can the online people hear now? Are the online people able to hear?
So let it be with Caesar.
Are you getting a text? Can anybody online hear? Yes.
Oh,
Okay, thank you.
you're good? Okay.
Okay. Am I good? Yes, okay. Good morning, I'm Srinivas Sakala from UNC Charlotte. I'm a little out of breath because I just ran in. So I'm sharing the session and my respondent co-chairs are Ken Elimelech, if I'm pronouncing the name correctly. He's a postdoc at Rice, working with Lydia Kavraki and Moshe Varty. And he works on task and motion planning and planning under uncertainty. And my second respondent co-chair is Everton Vieira from Rutgers. And he's a postdoc at DIMAX with Konstantin Mishchaikov. And his research interests are in topology applied to dynamical systems. So we have 4 speakers today. And our first speaker will be Sihui Li. Please come on down. So she's a PhD student at the Colorado School of Mines, working with Neil Denton, and her focus is on motion planning.
Hello, everyone. So here I'll present our paper. Okay, so motion planning plans a path from start to goal. A complete motion planner will return a path if a path exists, or it will tell you that a plan does not exist. But this property is very hard to achieve for high-dimensional motion planning problems. So people usually go for weaker notions of completeness. For example, widely used sampling-based motion planners are probabilistically complete, meaning that they can find a plan given long enough time, but it cannot tell you whether the plan is feasible or not. So in this paper, the focus is to tell you this infeasibility information along with a sampling-based motion planner. So before we get into more detail, why is knowing this infeasibility information important? Going from lab settings to real-world scenarios, motion planning is oftentimes a sub-problem to a larger problem. So if we don't know whether the plan existed or not, sometimes we face this dilemma. For example, with sampling-based motion planner, if it does not return plan, should we give it more time to plan, or should we try out a different task plan? Right. So without this infeasibility information, it will cause the larger plan to be incomplete or take a longer planning time. So here's the flow of this presentation. We will start with problem definition, then go to algorithm, then focus on the convergence analysis, then end with experiments. So first, our problem definition is a general motion planning problem setup. We have a configuration space, a start configuration and a go configuration. The output is a plan if a plan exists, or an infeasibility proof if a plan does not exist. So what is an infeasibility proof? If every path connecting the start and the goal has to go through some obstacle region, as is shown in this figure here, then the plan is infeasible. Right, so as is shown in this figure here, we have this loop closure that exists in obstacle region and separates start and goal. So formally, we define an infeasibility proof as a manifold that satisfies these three requirements. So first, it is closed, then it exists entirely in the obstacle region, and it separates the start and the goal. Right. So next let's go into the algorithm. So this is previously published in our other paper we'll briefly talk about here. So the algorithm has two main threads, the planning thread and the proof construction thread. The planning thread runs a sampling-based planner. Here we are using probabilistic roadmap, and it terminates the plan, terminates the algorithm, it defines the plan. And at the same time, it saves all sampled configurations, both in obstacle region and free space. And for the proof construction thread, it has two main threads, two main steps. Learn a manifold and then validate a manifold. For learning the manifold, we set up this classification problem where one class is all points connectable to the goal, and all other points are the other class. And we learn a classifier. So as you can see in this animation, as more points are sampled, the manifold converges more and more into the obstacle region. And here we are using radial basis function kernel support vector machine. We're using SVM because it gives us an analytical form boundary function along with other benefits. So after we learn the manifold, we validate the manifold. We do this by first sample points on the manifold and then triangulate using the sample points with tangential denali complexes. And then the result of this triangulation is this polytope shown in green here. And then we check each facet of the polytope to make sure that is contained in the obstacle region. So that's the algorithm. Next, let's go into the analysis part. So as you can see in the algorithm, we first learn the manifold and then validate the manifold. So all the rest of the step actually based on result of the learning step. So then here a question we want to answer is, if no plan exists, then will the learned manifold eventually converge into an infeasibility proof so that the rest of step would follow? And how fast would that happen? So in this paper, we proved that if no plan exists, then the probability of the learned manifold being an infeasibility proof converges to 1 as more points are sampled. So to prove this, we basically need to prove that the learned manifold follows these 3 requirements of an infeasibility proof. That is closed, it exists entirely in the obstacle region, and it separates start and goal. And this last statement is obvious since we're learning a classifier. This first statement will be natural after we prove the second one. So the key here is to prove that the manifold converges into the obstacle region. And to prove this, we identify regions that need samples and then calculate the probability. So here is the idea of this proof. We first identify this region that needs sample, and then if there are points in this region, it will push the manifold into the obstacle region. And here is more detail of the proof. We identify this region along the obstacle region boundary, and then decompose this region into this smaller, we call RI regions, such that if there is at least 1 point sampled in each RI region, then the manifold will exist inside the obstacle region. So if we are using uniform sampling, then the probability of failure, that is the probability of with at least one RI region with no sample, can be calculated eventually with this number here. That is, inside the parentheses is a number smaller than 1. So as n, the number of samples goes to infinity, this probability of failure converges to 0. So the probability of success, that is the probability of at least 1 point in each RI region, converges to 1 as more points are sampled. And as it turns out, we can put a tighter bound on the probability of failure by using binomial distribution. And applying Chernoff bound on binomial distribution gives us that probability of failure is eventually bounded by this negative exponential term with respect to the number of sample points. And this gives us our second result. That is, the probability of failure decreases to 0 exponentially. So to conclude a little bit, our planner, in the limit, it returns a plan or an infeasibility proof. This is different from probabilistic completeness because it returns this infeasibility proof. But it's also different from the original definition of completeness because it does not guarantee return in finite time since it's using sampling. So here we define this term asymptotic completeness. So a planner is asymptotically complete if it returns a plan or an infeasibility proof in the limit. And so here, let's look at some experiments. So we did 2D and 4D CN experiments to show convergence. And in the 2D scenes, we also compared uniform sampling with Gaussian sampling. Even though all the analysis is based on uniform sampling from the analysis, we can see that the important samples are around the obstacle region boundaries. And then Gaussian sampling produces samples near obstacle regions. Gaussian sampling should help the manifold converge faster, which is what we see in experiments. In both scenes is a start scene and a maze scene. The blue line is the Gaussian line, red dashed line is the uniform line. We can see that the Gaussian converges faster than uniform. We also apply this on this 4th squirrel arm scene. This, as you can see, with more points sampled, it converges, success rates converges to 1. And the dashed line is a fitted exponential curve. So some dirty laundry. First is analysis of the validation step. Remember that we have 2 steps with learning step and validation. The validation step analysis is mentioned in the paper, but it's not rigorously proved. So this is partly because we still want to improve this validation step. Important part of future work is extending to higher dimension, where a large roadblock is this validation step. So validation step takes a large majority of runtime in up to 4 DOF manipulators. And then along the years, we have went from 3 DOF to 4 DOF and now partially to 5 DOF. And we think this framework could work for higher DOF manipulators, but it requires more engineering and algorithmic effort. And here is a summary of our contribution. We have shown convergence and exponential convergence for learn manifold being an infeasibility proof. And we have defined this new type of completeness, asymptotic completeness. Right. And thanks. That's the end of it.
Next speaker is Niels
Wilde.
postdoc at TU Delft, working with Javier Alonso Mora. And he was earlier both a postdoc and a PhD student at the University of Waterloo, where he worked with Dana Coolidge and
Yeah, hello everyone. My name is Niels Wilde, and I'm happy to present our paper, Error-Bound Approximation of Pareto Fronts in Robot Planning Problems today. The paper was written together by Alex Botras, Armin Sadeki, and Stephen Smith from the University of Waterloo, and Javier Alonso Mora and myself from TU Delft. So let's jump into it. In many robotics problems, we face the challenge that we want to simultaneously optimize multiple objectives or features. So we want to find a solution that minimizes a set of different objective functions. And one of the most common approaches to these types of problems is that we use a linear scalarization, where we put weights on these features, and we then solve a single objective optimization problem that minimizes this weighted sum. An important question remains, how can we find good weights for the scalarization such that we recover a set of Pareto optimal solutions? That is the set of solutions where we can't improve any of the objectives without worsening at least one of the other objectives. And here in the figure on the right, we have an illustration when we use uniformly placed samples for scalarization. So here we have a motion planning problem with a Dubens vehicle, and we want to minimize trajectory length and jerk. And we then just put down weights like in uniform increments and compute the corresponding trajectories. And as we can see, a lot of these trajectories look very similar to each other. And if we look at the Pareto front, our sampled Pareto front points in blue are all in one area. So that's not a very good representation. It would be much nicer if it looked like this. And today I'm going to show you an algorithm that can compute samples for scalarized optimization that look like this. So why do we care about this? Why do we need good scalarization weights? The simple reason is that we can't compute all possible trade-offs in multi-objective optimization, especially not when doing this online. So what we often do is that we pre-compute a set of solutions, and this set should be as diverse as possible so that we can explore different options. And this has many applications. I just want to highlight two of them. One is reward learning, where we want to learn a reward function that represents a user's preference for how a robot should behave. However, most of the algorithms in reward learning require pre-computed trajectories, and having good trajectories at hand can help these algorithms. Another application is computing presets for robot behavior, for instance, driving styles for an autonomous car. Or if you have a multi-robot pickup and delivery problem, you want to explore the trade-offs between minimizing operation cost and maximizing quality of service. And since this problem is very cumbersome to solve, it's crucial that you spend your pre-computed computation time wisely. So let's define this problem. We begin with two simple definitions. The first is the weight set. So the weights in our scalarization shall be positive vectors where the elements sum to 1. And second, we need some error function to describe how well we represent weights that we didn't sample. For this, we use the notion of regret. And in short, the regret of a weight WA under weights B expresses how good the optimal solution for weights A approximate the optimal solution for weights B. With this, we can now state our main problem. So given a linearly scalarized multi-objective planning problem and some budget K, we want to solve this nested optimization problem. So let's break it down. We start in the innermost optimization, where we are given a set of pre-computed set of samples and the corresponding pre-computed trajectories or solutions that's shown in blue. And we're given some other weight where we want to approximate the corresponding optimal solution. That's the one in orange. So we then pick the one from our pre-computed set that does the best job at approximating. The maximization tells us that this orange solution that we want to approximate is chosen in a worst case manner. And now our job is to solve the outer approximation to pick a good set of pre-computed solutions. And all of this is subject to the constraints that we can't do more than k pre-computations. Okay, to solve the problem, we analyze the components of it. And first we take a look at this optimal cost, that is the objective value of our scalarized optimization problem as a function of the scalarization weights. And for any multi-objective optimization problem, this optimal cost is continuous and it's concave, with the only assumption being that these objective functions are bounded, so there's no infinities anywhere. Furthermore, we can compute the subgradient of that function by simply looking at the values of our features or our objective functions. So what does this tell us? Let's say we pick some weight W prime. Given that we have an exact solver for the scalarized version of the optimization problem, we will find the function value of this optimal cost function, and we get the tangent plane. And this now allows for a very powerful observation. If we want to approximate another weight, W star over here, using our pre-computed solution W prime, our regret is simply the difference between the tangent plane and that concave optimal cost function. So this gives us an idea on how we can use multiple samples to then approximate any other weight or the solution that is optimal for any other weight. So let's say we have n samples, where n is the number of objectives that we have in our problem. We can now bound this optimal cost function between the samples, and we can do that in two ways. We can do a linear interpolation of the objective values, the function values, which will give us a lower bound that holds because the function is concave. And we can take the tangents from both of these samples, which then builds a nice roof over the function. And the lowest of these tangents will give us a tight upper bound at any point. And so now by bounding this optimal cost function, we are able to bound the regret that our samples will have with respect to any weight that we didn't sample. Okay, so here's how that works. We now want to bound the regret in a neighborhood. We use the word neighborhood here somewhat loosely. A neighborhood is just a collection of n linearly independent samples. That's what's shown at the bottom of the figure on the right. We have three samples that we picked, W1, 2, and 3. And they now span a subspace, which is, they span a convex hull. And now we want to bound the regret of any weight that lies inside that convex hull. And we begin by just defining our interpolation plane. That's the red plane at the top. So just the interpolation of the three function values that we computed. And to then get an upper bound of regret, we take the difference between the lowest tangent plane and the interpolation plane, which will always be an upper bound for the difference between the tangent plane and the actual function curve. So at each point, for each neighborhood, we can bound the regret. And since this only requires like a linear function for the tangents and a linear functions for the interpolation, we can find the weight inside the neighborhood where the regret bound is the largest using a linear program. So this now leads to our algorithm. What we do in the end is a greedy minimization of this regret bound, of this upper bound on the regret in neighborhoods. And we begin by one initial neighborhood that's constituted by the canonical basis of weights. We then find the weight W prime with maximum regret bound inside the neighborhood and just add that to our set of samples. So we just pick the one that's now represented worst and add it to our samples. And then we divide the neighborhood in n smaller neighborhoods by just swapping in W prime for any of the weights that constituted that neighborhood. We then repeat that algorithm, but now over a set of neighborhoods. So we search over them, compute this regret bound, always just using a linear program, and then pick the one where the regret bound is largest, add that sample, and divide that one neighborhood further. So here's an illustration of how this works in a little example. We have two weights initially, the one at the endpoints of the function, and then we use our linear program to find the point with maximum regret bound. That's the weight W3. And we just add that to our set. So this will be our new sample. We now get two new smaller neighborhoods, the blue and the green one, and we compute the respective regret bounds in there. Green is larger here, so that's the next sample that we will be adding. And then we could continue from there and split all the next three neighborhoods into smaller neighborhoods, or we just stop here. And we are left with this piecewise linear approximation of this original function, and the error is now illustrated in red. That's actually the regret that we will have. Okay, how does this look like in a robotics problem? We go back to our example from the introduction with the Dubin's curves. And here again, we have the trajectories with the uniform samples and the output of our algorithm. Now we can take a look on the approximation of the optimal cost function. So in the left one, we have the uniform approach again. On the x-axis, we have the weights. So the tangents are just put in uniform increments over that function. However, when the function gets very steep, like at the right-hand end, the tangents lie very far above the actual function, resulting in a large error, resulting in a large regret if you wanted to approximate a solution over there. With our method, we use fewer tangents in places where the function is either almost linear or it's very, very flat. And we put more tangents in the area where all the changes happen. And that leads to a better approximation in that area and therefore to a better, smaller regret overall. Okay, we evaluated this approach in several different planning problems. Here's again a Dubin's planning problem, but now with 3 objectives: length, integral square jerk, and maximum jerk. And we compare the quality for approximating any possible solution using uniform samples and our samples, shown in blue and orange respectively. And let's just focus on the left plot and maybe on the center plot, left showing the maximum absolute regret and the center the relative regret, just the ratio, which is sometimes more interesting. What we see is that for different sizes of sample sets, our proposed approach always achieves a smaller regret overhaul, meaning that our solutions are better suited to approximate any solution that wasn't sampled. In another experiment, we looked how the output of our algorithm can be used in a reward learning application. So here we use reward learning using a framework learning from choice. So we want to learn a reward function from a user by showing them 2 alternatives at a time, and they pick the one that they like better. And so we do this over 10 iterations, and we hope that we will learn their reward function and then be able to compute an optimal trajectory for that user. And let's just worry about the colors, not about the different shades in it. So blue is using this simple, using an algorithm for learning from choice with uniform pre-sample. So we just uniformly sample a bunch of possible solutions and then give that to the algorithm. And orange is using our pre-samples, the output of our algorithm. And we observe that with our samples, learning is faster, and it actually is able to find better solutions. So if you use uniform pre-samples, your pre-sample set might not contain a close to optimal solution, so you converge to a local optimum. But with our set of pre-samples, we actually have a higher chance of finding the actual optimal solution for a certain user. Okay, with that, I'm at the end of the main part. So in summary, I presented to you an algorithm on how we can find good scalarization weights for a linearly scalarized multi-objective optimization problem. And we find weights that in the end allow us to approximate any trade-off in the linear scalarization. Of course, this is not the end of it. We have some limitations in our work. I guess the biggest limitation is that we require an exact solver for the scalarized optimization problem. And that's not always the case. So we want to extend the work in 2 directions here. First, we need to consider that we only have a suboptimal solver, but it will break our concavity result. So we need a mode, or like some little trick to repair the concavity so that our algorithm works. Secondly, if that suboptimal solver happens to be an approximation algorithm, it would be very nice if that approximation factor carries over into our regret bound. Secondly, we only focused on linear scalarization, which is widely used, but it's not Pareto complete. So you can't recover the entire Pareto front with a linear scalarization. Therefore, we also want to look into Chebyshev scalarization, which is Pareto complete, and adapt our algorithm to that setting. And finally, we also want to study the special case k = 1. So we're only allowed to pick one sample and solve this one-size-fits-all type of problem. The good news is the first 3 bullets, we are on a very good way of having answers for that. So the proofs are written out. We just need to write a paper about that. With that, I would like to conclude, and thank you very much.
Our next speaker is Brian is.
That you do.
He's going to talk about today, began and at MIT working with Leslie Patrick.
Test. Can everyone hear me? Take mascot to this. I'm going to be speaking to everyone today about motion planning with uncertainty over obstacle locations and extents. And let's go ahead and dive in. So just a little bit of brief background. So we're going to start out, we all know that motion planning can be a hard problem. We have a bunch of hardness proofs, but at the same time, we're often able to solve motion planning problems in practice. And there's a bunch of algorithms that are able to do this. We have sampling-based algorithms, optimization-based algorithms, search-based algorithms. And the basic idea that we have behind all of them is that there's a lot of the cases that we encounter in practice are not really the hardest possible motion planning problems. So there's a bunch of heuristics and different kind of algorithms designs that we have that are actually able to solve a lot of the problems that we see. Right, so the fact that we have these hardness results for motion planning problems wasn't kind of the end of the story there. We're still able to make useful progress. So, at the same time, we have prior results that say motion planning with obstacle uncertainty is in some ways harder than vanilla motion planning. And so one way that we can look at this is even if I give you a graph that I tell you contains the solution to this kind of motion planning problem, it still ends up being hard to find that solution even constrained within that graph. So we'll jump into a little bit more. But we have this problem becomes harder if you have obstacle uncertainty than the original problem was. But at the same time, we have these problems, so we still want to be able to solve them, right? We don't want to just give up. And that's going to be the focus of the talk today, is how can we make some progress even though we have stronger hardness results that are blocking algorithms that look similar to a lot of the algorithms that we're used to seeing. So let's go ahead and kind of motivate the problem in a little bit more detail. Say you're this robot and you want to get to the green dot, but your glasses are a little foggy, your sensors are noisy. You don't know exactly the location and shape of the obstacles that you're encountering in your environment. So the way that we're going to formalize this is that you have some sort of distribution that these obstacles are drawn from, and you draw the obstacle kind of once at the beginning of the episode, and the obstacle remains static, even though you don't know its exact location. And your goal is to find a path that has low collision probability to get to, in this case, the green star. And this, I want to point out a couple of little things that are going on here. So in particular, because you only draw the obstacles once at the beginning of the episode, say that you kind of stopped at some particular iteration and stay there for a while, say some number of waypoints. Your collision risk isn't going to increase, right? Because the obstacles are static, you're not moving, right? So we're going to lean into this assumption that these obstacles are static and they're kind of only drawn once. And kind of in particular, this turns out to give us strong correlations of what the collision probabilities are between points that are kind of close locally in the space that we're looking at. And so I also want to give you a little bit more intuition of why this problem is harder than the motion planning problem with known obstacle locations, and give you a little bit more intuition for the kind of correlations and collision probabilities that we might expect to see in practice. So let's take a quick look at the green dot and the purple dot. Each one of those is going to have an epsilon probability of collision with the obstacle that we see on our left. And the question we want to ask is, what is the probability that at least one of the two dots is in collision, either the green dot or the blue dot or both? And if we look closely at the obstacle, kind of the obstacle on the left, of which we drew a couple of draws from the distribution, we can see that, we have a good sense of the shape of the object, what the angle of that side is, but we don't have that good of an idea of what its extent is on the x-axis. That's really where most of the uncertainty is. And what that gives us is, we could go ahead and use a union bound and say, okay, one way that we can bound the probability that either the green or the blue point is in collision is say it's just 2 epsilon. But because we're mainly uncertain about this position on the x-axis, there's actually a strong correlation between the event that the two are in collision, right? Because if that obstacle ends up further to the right than we expected, we're more likely than not, both the green point and the blue point are going to be in collision. So kind of in this example, we can see that actually the real probability of that either the green or the blue is in collision is only going to be about epsilon. It will be a little bit more. So this kind of means that we have to be thinking quite a bit about the correlations in collision probabilities between points, especially ones that are kind of close in the space that we care about. So let's give an example that involves some trajectories and try to motivate a little bit why the kind of motion planning problem that comes out of this is harder, even if I give you a graph that contains the solution. So again, you're the robot, you're trying to get to the green star. And there's 2 paths that you can take. You have to take the green path to get there. But to get to the start of the green path, you can take the red path or the blue path. And the main difference in the red path and the blue path is which obstacles they interact with. The blue path, if you look at it in isolation, is a little bit more risky. But the red path interacts with that obstacle on the right, as well as the other 3 obstacles. And in this case, even though the individual, if I took and sum up the risks, the red path and the green path would be a lower risk path than taking the blue path and the green path. That ends up being kind of not the best, that ends up being a very loose approximation. The main risk of collision in these paths right here is that obstacle on the left. And because that collision probability is actually correlated between the blue path and the green path, it actually ends up being lower risk in this case to take the blue path and then the green path, right? Because instead of taking kind of a bunch of independent bets that you have good estimates of a bunch of different obstacles, you're essentially choosing, I only want to be risky with respect to a smaller set of obstacles. And that allows you to reduce the total risk of your trajectory. So, right, we want to lean into the fact that we have these correlations and take advantage of them to find trajectories that are both less risky and also not as conservative, right? Because we don't want to end up with a system that is just scared of going near objects because it's always afraid it's going to collide, right? So we want to have some sort of balance between the system being conservative and actually kind of having a low probability of collision. Now, if you're trying to go and do this kind of planning, right, you can say, okay, in this case, we don't have a lot of obstacles. We can just remember which obstacles we interacted with in the past, right? We can see, oh, that obstacle on the left, we've already been by it once. But it turns out that is exactly the thing that increases the computational complexity of the task. Right, it's the fact that in the worst case, and you can kind of construct reductions, and we've done that in a prior work, that show that you can actually be forced to memorize a bunch of the previous obstacles that you went by, and you can actually go ahead and take this all the way to constructing an NP hardness proof, right? But at the same time, right, does that mean that all the problems we encounter require long memory? Say that you're driving in some sort of parking lot and you're figuring out the path that you're going to take. You don't kind of remember every single car that you might go next to as you're planning some part of the trajectory that's way far out, right? Usually when you as a human are kind of planning these sort of tasks, you really only have to think about things that are local. You don't have to come back to these obstacles many times. So the idea here is that these problems don't all require long memory, and we want to design an algorithm that can take advantage of this and be able to quantify this. So for that, we define something which we call the collision horizon, which measures the complexity of a problem instance. So basically, it's going to be, this collision horizon is going to be a parameter of our algorithm. And when the collision horizon is going to be small for an instance, it's going to be an easy problem, and our algorithm can solve it efficiently. And when the collision horizon is large, we have a hard problem, and our algorithm isn't going to be able to solve it as efficiently. So the basic idea behind the collision horizon is it's in some sense a way of measuring of how many obstacles we need to encounter between interactions with the same obstacle. And this ends up driving kind of how much memory we need to have. So we have a little example here where we have these three obstacles. We have a sun, a cloud, and the moon. And in this case, the one thing that we're uncertain about, right? In this case, we know exactly where these obstacles are. We're just uncertain about how big they are, just for our cartoon example. So it might turn out that the sun is actually twice as big as we expected, right? And that's kind of where our collision risk is coming from. So if we go ahead and look at this trajectory right here, we can see, we're really only getting close to one obstacle of the sun, right? And the start and the end of the trajectory, we can see they're correlated if, the only thing we're uncertain about is the size of the obstacle. And in this case, because we're only interacting with one obstacle, the collision horizon we're going to say is 1. But if we wanted to go ahead and take this longer path that goes past the cloud, the moon, and then kind of around, we can see between the times that we return to the sun, we encounter 2 additional obstacles. And that makes our collision horizon 3. Because to properly solve this problem, we have to keep track of the obstacles that we interacted with, in the time between when we return to the sun. So very quickly, I'm going to give you an idea of what the algorithm might look like. You can think of it as we're actually just going to do a modified Dijkstra's where we kind of have an expanded graph. So in this case, we're going to go from obstacle 1 to obstacle 4, and we kind of divide it up into low risk regions or shadows, if you're a little bit more familiar with that, where if you kind of enter the dark blue region, you're going to enter a 0.05 probability risk, and if you enter the lighter blue region, you're going to encounter 0.01. But kind of once you enter that region, you don't really pay any additional risk. You kind of pay once for entering that region. Right, this is one way of capturing the correlation of probabilities that we have. For details of that, you should look at other works. But to give you a brief sense of what this algorithm might look like, is we kind of expand, okay, we can get from V1 to V2, we can enter the 0.05 collision probability risk region, we keep track of which region we entered. We can do the same thing for getting to V3, that's only 0.01. And we can see we can get to V3 going through V2, again 0.05, and then go make that step to V4. And now again, we don't pay for entering the 0.05 region again because we've kept track of it and we had already entered it that way. So basically keeping track of this memory allows you to not pay these costs multiple times. And for these simpler instances where the collision horizon is small, you can actually show that you come up with the optimal solution without having to keep a large memory. So a little bit of dirty laundry, right? I think this is, just the start of being able to come up with algorithms like this. In particular, our runtime is exponential with the collision horizon, right? So it works well when the collision horizon is small. It degrades, it becomes computationally quite bad very quickly as the collision horizon grows. Part of that is necessary. And then there's a related question of we have some experiments, but that's not a complete answer of what are all the domains where the collision horizon is small, and are there really different settings where collision horizon isn't the right way of measuring the complexity, and we need a different family of algorithms that's better suited for those settings. So we'd love to have a better understanding of that as well. And we also want to give a little thank you for Leslie and Tomas for kind of mentoring me and Luke throughout all these years. I actually did my PhD at a different university, and they were still supportive throughout that time and great collaborators as well. And just to finish things off, Really, I want to say that hardness is not a death sentence, but it does mean that we have to look at the problem a little bit more closely and understand what exactly makes it hard. Because if we understand what exactly makes it hard, we can find a way to work around it. And in particular, you can do this for motion planning with obstacle uncertainty, at least when the collision horizon is small. Thank you.
Thank you, Brian. Our speaker will be coming to us by video. And our next speaker is Michael Farber. He's a professor at the School of Mathematics, Queen Mary University of London. His research interests are in applied and computational topology, topological robotics, and applications of topology to statistics and computer science.
Can't shut him off.
I took the microphone off me.
Yeah. We have, I guess the room is small enough that if you have questions, you can just go. Yes.
Michael, hear me or what's the technology?
Oh, yeah.
Yes, he is online.
Okay, you guys start
Michael, first of all, I hope you feel better. Thank you for sharing this very valuable information with our community. One question which might embarrass myself, but I really need to understand it. If you have point robots and point obstacles as your specific example, can't I just move with straight lines and with probability 1, I will arrive from start to target without colliding with the point obstacles? Thank you.
Michael.
Can I answer? Can you
Yes.
hear me?
Please go ahead.
Okay. First of all, thank you very much for giving me opportunity to present this work, and apologies that I couldn't travel. So this question, which was asked, is a very good question. In fact, what we considered in our approach is idealized situation when the sizes are small. The sizes, we assume that robots and obstacles have 0 size. So actually, topologically, it makes the problem equivalent. It still keeps it equivalent in many ways to the problem when sizes are positive. Of course, but there are differences, and of course, if the obstacles have positive size, and if they stay away from each other for a certain distance, which you can estimate, then our approach is totally equivalent, and there is no problem with that. But when obstacles may have positive size and may approach each other closely, then indeed different approach needed. And technically, it will be not a vibration. This map, which we considered, will be not a vibration, but it will have some singularities. So yes, it is a different stage of this project.
Thank you, Michael.
Welcome.
Thank
Yeah. So my question for you, I really enjoyed your talk. It was also very clear. The thing I didn't quite get is you had the red, the blue, and the yellow and the green paths in the example, and you said the blue and the red, the blue is better or lower risk, but then when you combine that with the green, it is higher risk. And I didn't get where's the change? Why is it different?
Yes.
Why is it not composable in a sense?
Yes, so basically the idea was that between the segments, you had the correlation of collision probabilities. So if you remember that image well, there's that obstacle on the left, and the final segment, the green segment, always went close to that obstacle. So if you were, because you have to go close to that obstacle anyways, and it had that x-axis uncertainty, it wouldn't be that much marginal cost to go again kind of earlier in the trajectory. And that way, I believe it was the green one, the one around to the left, the main risk that it incurred was from that same obstacle. So even though if you looked at it just by itself, the green one that went by the left, if by itself it would have more risk than the other one, that risk was very correlated with the risk that you would see at the very end of the trajectory. Exactly. Exactly.
So Ms. Lee, so for asymptotic completeness, it was mentioned that it is asymptotically going to either return a plan or correctly state that the plan is infeasible. Is there any risk of incorrectly stating that a plan is infeasible? And if so, how is that resolved?
Right. So the definition of asymptotic completeness is that it either returns a plan or an infeasibility proof. As to the answer whether our algorithm is asymptotically complete, we have proof that the learning part will converge eventually to be an infeasibility proof. So it's up to the validation step whether it is actually a correct asymptotically complete algorithm. So then analysis of the validation step basically requires the triangulation to be iteratively smaller so that if one pass does not prove that the approximation polytope is in obstacle region, a smaller triangulation would. So that is the case with tangential dynamic complex and some other triangulation methods as well. So yes, I would like to say that our algorithm is asymptotically complete. But a rigorous proof of that definitely requires a rigorous proof of the validation step.
All right.
Yeah, so for the same paper, so have you tried in a space like SE3, and are there issues either with the dimensionality or because of its topology? And
yes, so
if I can have a second question too, are you making any assumptions about the smoothness of the obstacles so as to be able to make the proof?
There are requirements to the configuration space we need to work with. So we require the configuration space to be Euclidean, basically. We don't assume that it's a SE3 space. This is because we need to have special treatment for the boundaries of the configuration space. We treat the boundaries of the configuration space as with a thickness as part of the obstacle region. So that imagine if you have an obstacle region connecting two boundaries of a configuration space. In that case, you can still generate an feasibility proof. So that is one requirement of the configuration space. So your second question is regarding smoothness requirement. We don't have smoothness requirement, but we do have a requirement on the obstacle region of the configuration space. That is, the obstacle region cannot be infinitesimal small. Imagine that you have like a thin piece of paper in the configuration space, then our algorithm cannot guarantee convergence to that thin piece of paper. The obstacle region needs to have some thickness so that the manifold can exist in it. So that's so all of the requirements in the paper if you want to read it.
I had a question for the first speaker as well. So I believe that the results that you presented are for the case with just kinematic constraints with no kinodynamic constraints.
Yes. Yeah.
So I'm curious if like how you might extend the work to the case of dynamics. And I suppose like it might actually, it seems like some of the assumptions that you're kind of making, like the decision boundary should lie completely in the obstacle region would be different in this case. You might want to make sure to restrict the boundary to like the region of inevitable collision or something like that. Maybe you can comment on that.
Yeah, definitely one direction is extending to the dynamic case, but there is a lot of hardness in that direction right now. So for dynamic motion planning, one of the way to do that is to include all velocities, accelerations, positions into the configuration space, so that you have a much larger dimension configuration space. And then in that case, that would require more computational effort. Our framework currently, theoretically, it would work for high dimensional manipulators, but practically, it will work well up to 4 DOF right now. So that limits its application currently to dynamic case. Yeah.
Okay, so here's a question for Nils. Forgive me if I missed this, but I wonder if you can put any bounds on the regret that occurs as a function of the number of samples. Can you tell us how well it works as the number of samples increases? Can you quantify that?
Yeah, it just gets smaller. So let's say you have only one sample. You have like one shot, you have like one solution you pre-computed, and now you try to approximate either any other solution or there's an adversarial picking like the worst case thing. If you now add another sample to it, it can only get better. So your approximation can only become better, so the regret can only decrease with the number of samples.
Right, so I understand that it's monotonically decreasing.
Yes.
But the question is, can you say something about how fast?
Fast in the beginning, and then it gets slower. So that's what you usually see in the plots. Like, if the way our algorithm works is that we start with the canonical weights. So we only optimize for one feature at a time, which is not a good approximation for something that's in the middle for any like reasonable compromise. But that would be like the first thing that our algorithm would add. And then it leaves gaps between like the center point, like if it's 2D, like if the end point and the center-ish point doesn't need to be in the geometrical center. And then the next one you add is like at a largest error again. So in the beginning, you cut down the error bound quickly by just putting in the point in the most sensitive parts of your curve. And then it refines only after that. So it's, yeah.
Okay, thank you.
I have time for one more question. Should we
Great talk, by the way, I really enjoyed it. So regarding implementation of what we promote, augment. Is that the idea?
Exactly, and that's where you get the exponential dependence on the quotient horizon. And the quotient horizon is exactly how large subsets do you need. And there's a little bit of pruning that you can do, but that's the basic idea.
So the horizon is sort of a
Exactly. So the way that it's set up is that you choose the quotient horizon parameter that you're going to run the algorithm with. And then every instance, you can look at the optimal solution, without computing it, and you can take its collision horizon. And the ratio between the problem's collision horizon and the algorithm's collision horizon gives you a bound on how good of an approximation it is. And if the collision horizon you ran the algorithm with is better than the problem's one, you'll get an exact solution. So we get some software degradation as the gap between the two expands.
Great. Let's thank all our speakers.
Okay, great, thank you. I'm session chair for the keynote talk here. Feel free to these are my notes all about you. So I'm Michael Odie, I'm one of the co-chairs, and I have the privilege of being able to introduce you to Russ Tedrick. So Russ is a professor of many things, and we will get to that shortly. He's a professor at MIT, and he received his bachelor's in computer engineering from the University of Michigan, his PhD in electrical engineering and computer science from MIT. He's worked at a number of interesting places, including Microsoft Research, and the Santa Fe Institute. And one of the titles that he currently holds is Vice President of Robotics Research at the Toyota Research Institute. Dr. Tedrick is one of the first roboticists that I ever personally met. Sometime back when I was a young grad student and he was a younger assistant professor. I think, as all of you know, robotics is a very wide field. And if you look at Dr. Tedrick's list of affiliations, it really reflects this fact. So he is the Toyota Professor of Electrical Engineering and Computer Science, Aeronautics and Astronautics, Mechanical Engineering, and he did a postdoc at the Brain and Cognitive Science Department at MIT. In addition to all of those affiliations, he's a director of CSAIL, and other notable accomplishments include the NSF Career Award, the DARPA Young Faculty Award in Mathematics, Microsoft Research New Faculty Fellow, and he has multiple teaching awards. Other kind of notable stuff that you're probably familiar with, but is kind of interesting to talk about, is that he spearheaded the Drake software package, and he led MIT's entry in the DARPA Robotics Challenge. This is the humanoid one. And a notable thing about that particular effort was the use of machine learning in his particular team's stuff that was in that competition. So on a personal note, I have always followed and admired Dr. Tedrick's work, and my lab's own paper here at WAFR is actually built on some of his LQR tree work from a while ago. So he's done extraordinary work in humanoid locomotion, among other things, and both at the theoretical and experimental kind of ends of the spectrum, which I think is very impressive. One of my personal favorite interactions with Dr. Tedrick was actually an exercise in applied human locomotion, which I will talk about, even though this is a kind of more theoretical conference here. And that is when he organized a small group of us to go running with him on his local commute from work home along the Charles River. And I've always wondered how much his research in humanoid locomotion and his personal experience with distance running kind of interact with each other and influence and inform each other. So I'm excited to see what he's been up to lately. It's my pleasure to introduce our first WAFR keynote speaker of 2022, Dr. Russ Tedrick.
Thank you, Michael. That was a great introduction. I really appreciate it. I'm not the director of CSAIL. That's Daniela. There's a CSAIL Center for Robotics. That's a much smaller ask. So I'm really excited to be here today because there's a set of results that we've been working on that I'd like to tell you about. And I think this is really maybe the best audience to help vet these ideas and to think about these ideas. So instead of trying to give any sort of broad coverage of the kind of things we're thinking about at the MIT group, I'm going to tell you about this one set of ideas about motion planning around convex optimization. And I'm going to take the time allotted here to try to teach you some of the details of that and step through. And I hope you'll give us good feedback and ask good questions. So in particular, there's two papers that are the 1-2 combination of work here. The first is shortest path on graph of convex sets. It's joint work with a few people. This is Pablo Perillo. Tobia is here in the audience, and you should address questions to either of us throughout the week if you have them. Okay, so the goal of the work, of course, is motion planning. I don't have to sell that to this audience. In particular, I'm interested in the questions of global motion planning and global optimization-based motion planning, in particular of systems with dynamic constraints. This is motivated for me thinking a lot about planning through contact. We want robots that can pick up objects or walk or run down the Charles, I guess. But today I'm going to actually just narrow it. We're not going to do all the way through contact today. We'll just talk about collision-free planning. And I took one of the old goody animated GIFs to say that. But also there's maybe a deeper goal for today, which is I think there's a lot of different ways that people think about planning. Maybe even in this room, there's a lot of different ways that people think about planning. You might be a trajectory optimization type person, a sample-based planning person, a logical planning person, or a combinatorial optimization expert. And to some extent, we're all talking about the same truth. And so there must be some connections here and try to I'm very interested in making some deeper connections across these different disciplines. And I hope we can give you one example of that today. And so maybe as a litmus test of which of these you are, right? So if I think about this problem of just finding a path through a maze from the start to the goal, it's kind of interesting to see different people's reactions to this, right? So if you're a theoretical computer scientist, you think about graph theory a lot, you'd say this is a trivial problem. There's a trivial graph that lives on this. I can just do search in the graph. But if I say, okay, well, I'm actually going to fly a quadrotor through here. I want to find a continuous path through this. If you're a sample-based planning person, you say, well, I can, it's in 2D, I can sample enough, it's no big deal. If you're a trajectory optimization person, you're probably running for the hills. This is like a terrible problem for trajectory optimization on the face of it. But there are other problems, like those problems that we've been thinking about with dynamics, and they're relatively high dimensional state spaces, dynamic constraints. This is where trajectory optimization really shines. These one trajectory optimization recipe, you just change a few parameters. You go from running to walking to bounding, galloping, right? This is beautiful, smooth motions of a high dimensional, highly constrained system. And the sample-based planners would struggle more in this. I mean, some of you in the room have done very good work in that direction, but it always feels a little unnatural of trying to jam in dynamic constraints into the sample-based methods. So can we find something that sort of blends some of the best of both worlds? So I want to talk through that. Let's start with just thinking about the motion. I'm coming mostly from the trajectory optimization side of that. So I want to walk you through from that direction through this idea, starting with motion planning as optimization. And I'll use just a very simple example to make the point, a little running example here of moving around a red obstacle box here from the start to the goal. Because actually that's enough to make many of the key points I want to make. So let's first just think about the way that you would typically write that as a trajectory optimization problem. So we'll break it down here. So we have a cost function, which is just the sum. Well, first of all, we have a bunch of sample points that we're going to make, x0 through xn. We have a cost function, which is the sum of the squared distances, which is kind of a weird cost function, but it's a common one. Okay. We have an initial condition constraint, a final condition constraint. And then we have this collision avoidance constraint saying that for all of my samples, I'd like them to be outside the box. And in this very simple example, I can just write that as being outside the L1 ball, okay? Which is as simple as it can get for collision avoidance, but that's good enough for now. Now, this problem is clean except for this collision avoidance constraint. This is a non-convex constraint, okay? And this means that trajectory optimization based on gradients or second order kind of methods, anything that's based on local analysis of the optimization problem tends to struggle. And I'll just run a little example here to make that point. This is a little code that's running, and I've got an animated interface in the web here to do that, okay? So let's say I've got a start to the goal. To keep it super simple on the slide, I didn't worry about the segment colliding, only the points colliding. So I get a some nominal solution to that optimization problem just using a standard gradient-based optimization. And I can move it around. And the frustrating thing, I mean, it solves in real time, it's no big deal, this, even for bigger problems, okay? But the problem has local minima, right? So in particular, when I start bringing the initial condition over here, of course, there's obviously a shorter path that goes around the other side, but no matter what the system's just stuck, right? You have to get worse before you can get better if you want to hop over to the other side. It's a classic case of local minimum. Okay, so let's try to fix that. And that's basically the story of the talk, is we're going to try to fix that in some fundamental way. There's one other thing that I don't like about that formulation, I've always not liked about this formulation, is this need to pick the finite number of n before you start. That's, it can be a little awkward in your optimization, but I actually think it makes the problem, it's an artificial constraint on the problem that maybe makes the problem landscape worse than it should be. So we'd also want to get away from that. Okay, a preview of the results here. So nowadays, we can have algorithms that will solve trajectory optimization for dynamical systems to global optimality. I'm going to qualify this very carefully as a trajectory optimization problem. And it's actually even a convex trajectory optimization problem. So that local minima we just talked about, somehow I'm going to try to give you a solution around that local minima problem that works out. And it works for simple cases like this, but it also works for pretty complicated systems. So this is a quadrotors flying through randomly generated, mazes, if you will, obstacle courses with differential constraints, or even, pretty complicated bimanual manipulation problems. Right, so if I have to put the mug on the shelf and I've got two big arms that have to stay out of each other's way, that configuration space obstacles are pretty tough. Right, this is like playing Twister with your EWAs, okay? That's actually coming out of a convex optimization. Okay, so the puzzle then is how the heck does that come out of a convex optimization? Okay, and the key ingredients are to combine an optimization perspective of graph search in the discrete world with an optimization perspective on trajectory optimization in the continuous world. And these things, again, they're trying to solve the same problem in some sense, and we just trying to find new ways to put those two insights together. And continuous motion planning as a convex optimization, there's lots of work in kinematic trajectory optimization. For quadrotors, there's the famous minimum snap trajectory generation. Okay, so it's really finding a good way to put these two together that leads to tractable convex problems that solve very well. So let me get to that with one more intermediate step. Let me tell you a way to solve the problem globally as a mixed integer convex program, okay? So we can write the same problem and solve it to global optimality with existing tools. It's just that they don't scale very well. But the way those tools work is I could say, here's my same cost function, my same initial conditions, but let's write the obstacle constraint differently. If I want to break down the space and say, well, I'm going to be, some of these samples have to be outside that face of the obstacle, or they have to be outside this face, or outside this face, or outside this face. That's another way to write that constraint. You can write those as disjunctive constraints or constraints, right? And then you can actually cast that into an optimization problem that we can solve very well by using integer variables on those logical ors and those disjunctive constraints. Okay, so let me just make sure I land what a mixed integer program is. So a standard optimization problem that has some continuous variables and some discrete variables that I'm going to do mixed binary, okay? I can have a cost function, I have constraints, but I'm going to have one additional constraint that these b's are just take values 0 or 1, okay? And we call it mixed integer convex if f and g are convex, okay? But this is obviously a non-convex constraint, okay? And we talk about this, the convex relaxation of that problem if we replace this 0 or 1 with between 0 and 1. So that would be the convex relaxation. Okay, and that's most of the hard work we've done here, but there's some particularly nice mixed integer problems In particular, we can say that the convex relaxation is tight. This is the dream, is to say that the convex relaxation is tight, which means solving the relaxed version of the problem actually solves the original problem. In the best cases, you can find a formulation where you don't have to worry about the fact that they're integers. You relax it, you get the same answer. Okay. The way you typically solve a mixed integer program is with a branch and bound algorithm, where you would start by, at the initial problem, just relaxing the constraint completely, take all of the b's and just put them between 0 and 1. That's a convex problem. That's the great thing, is if I make any binary assignment, the rest of this is a convex problem if it's a mixed integer convex. And then I see this value, oh, this one's not, it didn't come out to be 1, it wasn't tight, but it's close. So maybe I'll try making b equal 1, or depending on what those values are, I'll round it to 0 or 1, and eventually I might have to check both cases. And then after that, I can solve other convex problems with subject to that some new constraint, b equals 0 or 1, and I can go down this search tree. Right? And so through exhaustive search, you can certainly find the optimal solution to this problem, because there's a finite number of elements and everyone's convex. But the important property of this is that if every convex relaxation you solve provides a lower bound, right? You've relaxed something, so you get a lower bound on the optimal problem, and feasible solutions provide an upper bound. And if you combine this recipe, then actually you don't have to go through most of the tree. In most problem instances, you don't explore the 2 to the n possible permutations. You're able to just immediately say, going down this tree is not required because I've already found out a lower bound and upper bound such that I don't have to just even look at that whole tree. You just eliminate entire subtrees. Okay, so in particular, you can think about that as like now the property of these branch and bound algorithms, of course, the runtime is going to depend on the number of integer variables, how big your tree is, okay? But it's also going to depend a lot on the tightness of the convex relaxation. If you have a relaxation that is very close to tight, then it can very quickly rule out huge parts of the search space, right? So you don't actually have to, you can explore much, much less of the tree. Unfortunately, if you look at the motion planning, the way we typically transcribe, our group, for instance, for the last N years has typically transcribed motion planning algorithms into mixed integer programs. They're not on the good end of this. They typically have too many integer variables in the sense that, there's sort of an obvious combinatorial complexity, a topological complexity of going around that obstacle. You can go left or right. But we're saying every sample might be against every face. It's artificially way more combinatorial than the real problem is, okay? But also the disjunctive programming leads to loose convex relaxations. So let me try to make that point here. So there's a bunch of ways you can do the mixed integer. I've got big M, I've got convex hull, but I'll just do the big M here now. So if I run this big M formulation of one of the mixed integer formulations of these constraints, then now I have a new solution that solves the global optimality using a simple branch and bound algorithm. It's perfectly runtime in the small example, but it scales badly as I get much bigger. Okay, but here's the killer, and this is, I think, the reason. It's not only do we have this artificial combinatorial complexity. Oops, wrong screen. But I put in here whether I just show the convex relaxation or the full problem. But if I change this to say, let me show you just the solution of the convex relaxation, just the top node of the branch and bound, then what happens, okay? Then the convex relaxation of these disjunctive programs, no matter how you write them, big M, convex hull, or whatever, they're kind of not capturing the essence of the problem. I don't want to use a derogatory term, but they're not getting it, right? So almost always, if you say, I could have been here or here or here or here, the relaxation just goes right up the middle. And this is, I think, the symptom of it, that's causing these relaxations to be very loose and the runtimes to be very long. Okay, so how can we do better than that? Pablo, fantastic collaborator, has really changed the way I think about a lot of things, okay? Tobia and I were talking to him about how inefficiency of our contact planning and the looseness of these convex relaxations. And he asked the right question one day. He's like, hold on a second, we know from graph search some convex programs where the convex relaxation is tight. Why the heck are your relaxations so loose? Okay. And so we started to put them side by side. Okay, let's look at the discrete optimization. Let's look at the continuous optimization. And we realized there were some things we were just doing wrong. And the connections are actually really, really nice. Okay, so let me take a quick side trip and say, how would you do an optimization-based approach to graph search? Okay, so I'll just make a standard discrete graph with vertices V and directed edges E. Okay, and the problem formulation actually looks a lot like what we just did with the mixed integer. This time I'm going to put binaries on the edges. So if I'll put a 0, 1 variable for every edge, and I want it to be 1 at the solution if the edge is in the shortest path, otherwise 0. Okay, and I can make it a weighted graph, so I can put an edge weight if I want to do shortest path, weighted shortest path. So the cost function then is just the sum of the weights of the pieces that are on. And then the graph constraints that make sure it's a path are just these flow constraints, which is basically the sum of the flows going into every node equals the sum of the flows going out of the node. You'd hope that they're either going to be all 0, the sum is either 0 or 1, depending on if the flow goes through that vertex or not. Okay, and then you would think I would write now that phi would be 0 or 1, but it turns out in this problem that you don't need that if you just write greater than or equal to 0 or greater than or equal to 0, you don't even need the less than 1, that this solution is the convex relaxation of the mixed integer program, but it's tight. The linear program solves the optimality, finds the optimal solution of the combinatorial problem. Okay, so that's a well-known result, but we see put that side by side with our formulations, and you think, what are we doing wrong? What's different? Okay, well, the weights are on the edges. That seems like an important thing. There's a couple other nuances that we'll talk through. So that led to a generalization of thinking about how do we combine continuous optimization with these discrete searches, and this graph of convex sets is the generalization. Okay, so now we want to think about a continuous problem, a mixed discrete and continuous problem. Every time I visit a node in the graph, I'm going to pick one element out of a convex set. Okay, so that's it. So these are little islands in this case, not obstacles. Think of them as islands. We'll get back to obstacles in a minute. Every time I visit this, I pick one element inside this set. And then by visiting this node, I get to pick, and those elements are in the shortest path. Okay, I'll let the edge length now generalize from a constant to being some convex function of the continuous variables. That turns out to be a rich prescription. I'll show you how it plays out in motion planning. Okay, and now you can take the original classic shortest path linear programming problem and turn it into the convex sets. It makes very few changes. I've generalized the cost to be a function now. And we've added one extra thing saying that those elements are picked from inside each of their relative sets. Okay, but it's almost identical otherwise. This objective, if you're trained in the ways of convex optimization, you'll recognize, even though it looks non-convex, because I've said this is convex, but I'm multiplying it by another variable. Typically bilinear things are non-convex, but this one, because it's greater than 0, it turns out there are ways to recast that. That's a well-known tool. Perspective functions will let you do that, but if you have a non-negative scaling of any convex set, then that is still a convex set. Okay, so this can be written as a mixed integer convex program. And by doing that, we achieved orders of magnitude speedups in our original problem. Okay, already. But there was more to it. So Tobias went back and started trying to find exactly, he started really studying the convex relaxation. Now we are saying the convex relaxation should be good. So he started making very simple graphs and trying to understand when was it light, when was it tight, when was it loose, really going through. And there were a couple examples in particular where Pablo was like, you're missing if that one's not tight, you are missing a constraint, and which was an interesting insight because I wouldn't have said that, but Pablo very much had the attitudes like, if you can see a trivial lower bound that the linear program isn't finding, then you missed something. Linear program should always outsmart you, right? Which is was super useful, and sure enough, on more investigation, we found the missing constraint, right? Okay, and there's a family of constraints that you can add to the problem. Which it's interesting, they don't change the optimal solution. It's not that we missed a constraint in the sense that we got the wrong answers, but you could add extra constraints which don't change the optimal solution, but they change the relaxation. And the one that I'll highlight here, which is I think a key one, is that if you think about these conservation of flow constraints, the flow coming into the node has to equal the sum of the flows coming out. There's a version of that which is the spatial conservation of flow, where you multiply the continuous variables. The actual version uses slack variables, but approximately this, okay, which allows us to say that the continuous variables are also affected by this flow constraint. Okay, this was the missing set of constraints, and it made a huge difference in the quality of the convex relaxation. Okay, so this is now how we would write the motion planning around that simple problem with the graph of convex sets. We can take those disjunctive constraints, but we're actually going to write them differently now. We have this sort of graph structure of there's left or right around the obstacle, and we're capturing that real combinatorial complexity more natively, okay? We can still write our convex loss functions, and we now just formulate this graph search on top of the continuous search. Of course, I'll run the example. Here's the graph of convex sets version. And the number of decision variables was not preordained. That's kind of nice because it's the path length in a graph search problem. Okay, and it solves the global optimality. That's not surprising. But the important point here, gotta stop this. The important point here is I'm going to change this now to show you what's the convex relaxation. Okay, and this one is still tight, okay? Which isn't too surprising for this very simple example, but we're gonna see it works even for much more complicated examples, okay? So back to our maze. Now we're gonna find a continuous path. Oh yeah, please.
Can I ask a question?
Please, yeah.
What is the definition of how to decide which convex set to choose to design the relaxed formulation?
Good. So the question is, how do I design the convex set? In the maze example and some of the simple examples, there's a natural convex decomposition of the space, and I'm trying to use that for the beginning examples. I'll show you the harder examples. There's a more complicated story when it's the arms going through and everything like that. That's a fundamental question that I'll try to address. In this one, it's easy. You can just make a box for each cell. Okay, I want to go from the start to the goal, but I want to find a continuous path. Like I'm going to walk a humanoid robot through here or something like this, right? It turns out the continuous path by some metric of path length is this. And that's coming out of a convex optimization. The convex relaxation is tight in that setting. Like when I first saw that, I thought, that's not what convex optimization should do. But it connects it's just connecting the discrete graph with the continuous optimization. And by the way, the previous formulations would have been intractable for this. Just the number of binary variables was insane. So you can make problems, the convex relaxations tighter by adding exponentials of numbers of constraints. That's not what we've done here. We've added an efficient number of constraints and got good relaxations. Okay, so I knew there was a session on hardness results and everything before us. So this is not changing. It's not defeating any hardness results, of course, right? In the particular example of this Euclidean shortest path, kind of like we showed there, there's a lot known about the hardness of that problem. This formulation provides a polynomial time algorithm. It works in arbitrary dimensions, and it is often tight. Okay, we're not saying P equals NP. We're just saying that in practice, it's almost always tight, but we know counterexamples where it is not tight. A bit like what Brian was saying. Okay, and it does solve a more general class of problems than the standard Euclidean shortest path problem. It's got some nice properties. So like if I take those sets and I shrink them down to a point, then I actually get back the original formulation. So we haven't broken this known good result. We know there's instances that are NP hard. We have all simple examples in the paper of all of the corner cases, if you will. But you can do interesting things with this. So it's a pretty expressive language. So you can, for instance, put constraints in the cost. So we allow our costs to be infinite. So that means you can sort of implement constraints in the cost. And so you can add dynamics into this, for instance. And one of the first things we did was we took some of our old mixed integer footstep planning and we solved them much, much faster, orders of magnitude faster, many orders of magnitude faster than our previous approaches. But let me tell you about the differential constraints for motion planning. Okay, so here's the way I'm going to transcribe the motion planning problem down into a graph of convex sets. So now the red is the obstacle, the blue are the sets we want to stay inside. That's a convex decomposition of the space. Again, a simple example here will make the more general case. There's a natural graph. If I just make an edge in the graph for every, if the sets intersect at all, even on a line, measure zero intersection, but if they intersect at all, I'll put an edge in the graph. And I'm actually just gonna put an edge both directions. I could go either way, right? This is my source, this is my target. So this gives me a trivial graph. And then I'm not gonna find one point in each set. I'm gonna write an entire curve that lives in the set. So the graph of convex sets actually lives in some Cartesian product of those sets up in some high dimensional space to represent the curve, okay? But pictorially, I can just say we've got a curve that is constrained to live inside each set. If we use Bézier's curves, then we can use that with linear constraints, convex constraints. Okay, and then at optimality, we'd like to have those, we have constraints so that if this edge between here and here is in the shortest path, then the final node in this curve has to touch the final point of this curve up, and we can add derivative constraints on that, for instance, up to some derivative smoothness. And then there's one more thing is we can't preordain the smoothness or the timing of this. So we actually have another curve that lives in each one of these sets that thinks about a time rescaling that works along with it. And we solve those all jointly in a convex way. So this is the kind of, like, if you're thinking, oh, could I use this? Here's the set of cost functions that we support right out of the box. So you can have a duration, a total path time. You can have a path length. You can have something about path energy. We have other terms that we can put in for smoothness. Then you can ask for it to be differentiable up to some degree. You can have your collision avoidance constraints, saying that all of my Qs are in the union of the safe sets. And unlike most of the sampling-based approaches, this is actually for all T. We're not saying like at some sample points, this is an absolute, that curve is outside the obstacles. You can add velocity constraints. Acceleration constraints, we don't have yet. They're tough. They come in a non-convex way given our time rescaling, but we'll figure those out at some point. Then you can put bounds on the total time. You can put initial and final conditions. Okay, so that's kind of the library of optimization problems we can write in this format now. And if you solve that now, solve the maze problem. This is not actually. We downloaded a bunch of mazes and then we realized mazes all have like one solution, right? So we had to knock walls out of the mazes in order to make it interesting. So there's multiple paths and multiple solutions. And if you change your objective function from minimum distance to minimum time, you get different paths out of the same graph, right? And they're solved to optimality. So just to say it, I'll repeat it a few times just to make sure I don't try to give the impression of something more than it is, right? So we have a transcription to a mixed integer convex optimization, but with a very tight convex relaxation, right? So we're not saying P equals NP, we're saying we can solve the global optimality with branch and bound, orders of magnitude than with previous work. And in fact, it got to the point where it's so good that we basically never solve branch and bound. We don't even say you need a branch and bound solver. You can just call the convex optimization solver. We've got some rounding strategies that will take an approximate thing and make it very good, and this is almost always sufficient to obtain the globally optimal solution. Okay, now that is something that is somehow an empirical statement, like that in many problem instances, it's almost always good. So let me give you an empirical evidence for that, okay? So we started making random environments for a quadrotor, and we did the planning from start to a goal, and we just started to collect statistics given this randomly generated environments. How often are we optimal from the convex relaxation? And there's actually two different plots here. So this one, the optimality gap is we're going to solve the convex optimization, and then we're going to solve the mixed integer convex optimization and see when are they the same and when are they different. And basically, almost always they're the same. You get the optimal solution. And even when you don't, in all of our examples, you get like 2% off optimal. Like you flew through the neighboring window instead of this window. So they're really, the optimality gap in practice seems to be very, very small. There's a second question, which is if you only solve the convex optimization, can you know that you're optimal just from that without solving the mixed integer, right? Because that was the thing we wanted to avoid in the first place. You just use the lower bound and the rounded solution of the convex optimization to give a bound. And you can ask what's the gap of that lower and upper bound. And that certified optimality gap, solving only convex problems, is also very good. It's not as good as the true, in practice, it performs better than it can prove it performs. Okay, but it's pretty encouraging. Okay, how do we get to convex regions? Here's the big question, right? So the way we've done it in the past is we have approximate convex segmentation algorithms, which scale, they use an iteration between quadratic programs and semi-definite programs, and they scale to high dimensions. At the time, we were doing it with raw sensor data, so we really wanted that scaling to work. And this is a general approach that we're going to extend. And so the way you should think about it is you can do a bit of sampling. You have your initial region for your quadrotor, for instance. You have some bounding volume that you care about, and you'll just start drawing samples. But instead of building some dense map, dense road map, for instance, every time I make a sample, I'll grow a big region around that sample, and I'll come up with a small number of convex regions that tries to fill the space. Okay, and then you do the planning through that. Now, in configuration space, I showed you robot arms that have complex, configuration space obstacles. In configuration space, in the previous work, we assumed the obstacles were convex. You can't assume that in configuration space. So we've now been generalizing that algorithm to configuration space. There's two generalizations of it. One with not just nonlinear optimization that's very fast, but not certified, and then another one that does sums of squares optimization to rigorously certify. And there's a presentation on that. Alex will give a presentation on that, the details of that on Friday. But in particular, it's surprisingly effective, even in these complicated configuration space. So you take the sums of squares certificates, for example, of a bimanual, two-armed thing, and you ask for a proof that these things are out of collision. It's showing the details of this will be crystal clear about it on Friday, but it's trying to show that this separating plane is separating these two convex bodies in task space. And the point is that they're getting very, very, very close. It's not like we're making some coarse approximations, over here, but we can't say anything when things get tight. It's actually finding, with small numbers of space of regions, pretty good coverage of the space. Okay, so let's connect this to sample-based motion planning. So, the classic PRM, I like to use the old picture from Howie et al. So you all know what a probabilistic roadmap is. So the proposal here is almost the same, but the problem, I guess, with only using points and line segments in your roadmap is that doesn't leave any room for optimization when you're done. So the proposal here is every time you add a point, just grow the region. And instead of making 10,000 points inside there, make 10. And you can actually then leave yourself room to do continuous optimization inside the set, get beautiful guarantees, actually more guarantees than you can get in a sample-based approach that's only checking at a finite number of points. And within that convex decomposition, we can solve with the branch and bound to global optimality, or almost always with the convex relaxation. Okay, so So we did a bunch of comparisons of just like how does the graph of convex sets formulation compare with PRM, for instance. I think that is the natural comparison, is because we're going to spend offline computation building the regions, and we want our online computation to be fast, similar to a roadmap multi-query kind of approach. Okay, and we compared it against PRM, and PRM with shortcutting, which of course has longer solve times, but better paths that comes out. Okay. It's interesting too, that part of this work was motivated by thinking about, there's a lot of companies out there using robots to do, they're working in the same environment almost all the time, right? Whether it's scooping salads, my friends at Dexi are scooping salads all the time, and their workspace really doesn't change. Their motions change from time to time, and so the paths have to change, but the configuration space, you could totally pre-compute that, and you should, I would think. Okay, so again, statistical analysis here. So different tasks is just going from different points in the state space, in the configuration space to the other. And if you compare the trajectory length of the graph of convex sets versus the PRM versus the shortcut, we not surprisingly get shorter paths. The PRM here was actually 10,000 points, right? And the graph of convex sets took 8 sets to pick. And we used all the same points. We tried to be super fair to the PRM, like all the same points we used to seed the regions were also in the PRM. We used RRTs to connect, give it every possible advantage we tried to. Okay, and the shortcut does better, of course, but is not optimal in most cases. And then the runtime is mostly comparable. This is now much more subjective because it depends how much we optimized our PRM. This is just on a CPU. It's not on it's not a GPU or FPGA or anything like this. Okay, but we have comparable, competitive, I think, runtimes, and those are going to get better. I actually really like this one, right? So there's one case where the solve time was almost 0, and the reason for that is actually a clever preprocessing algorithm that Tobias came up with. That basically, just looking at the discrete graph, if you can prove that you don't need to visit a bunch of cells, you can trim the graph before you start. And so, in a good way, you actually find when there's just a short path to the goal, and that's all you need to do to explore, then it makes the simple instances fast. Yeah, so it works for lots of different robotics sort of applications. This is the bimanual one again, just to show how tight that is, and it's solving. So we did not compare this one to PRM. PRM, I think. It's hard to get to work in 14 degrees of freedom, right? Takes many, many samples. Most people will, when they have a bimanual mobile manipulator, for instance, they will kind of plan with one arm or plan with the other arm, but you hold the other one fixed. So this is something that I think is a good application for graph of convex sets, is we can plan in a few seconds, even on the bimanual cases. Okay, so I talked about the motion planning instance, okay, but it's actually a more general framework, right? Tobias looked at a bunch of different mixed combinatorial continuous optimization problems. Oftentimes, not in every instance, but there's a number of problems where this is a kind of a nice way to write the problem down, and you get tighter convex relaxations. I think for task and motion planning, there's a natural, again, relationship between the discrete decisions and the logical conditions and the continuous optimization that I think we're not exploiting that connection in a deep way yet, and we can. This is version 0.1, I would say, of a framework, right? So I think, I hope you all get excited about it, help it grow, but it's competing with tools that have been optimized for a long time, and this is just the first version. I would say, compared to the RRT, for instance, it's hard to implement. It's not, it's not a few lines of code. It's built on a tool chain which has made the mathematical abstractions of perspective functions and everything good. It's clean, but it's harder to implement, harder to type in yourself. You should, totally possible, but just a little bit more sophisticated. So I think in order to make it useful to everybody, we've tried to provide a mature implementation, and hopefully you'll check it out. There's a lot more we're currently doing and we want to do. For instance, just generalizing, we start to talk to people who are actually would consider using this, and they say, okay, well, we want end effector constraints on velocity, and we don't want to spill the salad when we're moving, and there's just other constraints that you want to put in. Dynamics are a particular case we're working very hard on, but I just left that out of this first presentation. But also, I think there's a lot of reasons to be optimistic about the solve times. The work we showed right now is just handing it to a standard custom solver. But this problem is sort of dripping with gobs of structure that you could, that we don't know how, in the current way that you talk to a convex optimization program, we can't, in the interface of like A and B matrices, we can't tell it about all the structure we know from the graph. So I think there's a lot of room for that, and we're starting to work on custom solvers. Or you can warm start it. For instance, if you're really executing very similar trajectories lots of times, I think you could just have that small runtime almost all the time. So we put that mature implementation in Drake, and I have to just tell you for a second about what's going on in Drake. So Drake is a couple things. It does have a good simulation engine, a physics engine, compared to for manipulation. I think it's got a very rich contact modeling library, an approach to contact modeling that is, I think, better for simulation and for optimization than a lot of the standard approaches. In particular, where most people who are simulating contact, including us for many, many years, you'd always summarize the forces between two bodies with point forces. And this is just a fundamentally bad operation. And we're doing more work these days inside Drake to do, just take the extra work of thinking about the entire penetration of two bodies, finding a surface integral and just taking, the force calculation integrated over that entire surface. This makes a huge difference in terms of smoothness of the simulation landscape and optimization landscape. Okay, so for manipulation and for sim to real manipulation, I think it's state of the art. And inside there's lots of, this is now where we put our mature code. So if inside Drake, there's an optimization hierarchy, you can interface with your favorite optimization engines through this, and you can you can call it the graph of convex sets and just build up your graph saying, here's a node, here's a node, here's a node, here's an edge, here's my costs on that edge and constraints, and boom, go. It'll solve, if you have Gurobi on your system, it'll solve that. If you have MOSEC on your system, it sort of does all that work for you. And I hope that will reduce the barrier of giving this a try and extending it. Okay, so I wanted to tell you, about one real thing here, which is this new strong mixed integer convex formulation for shortest path problems over convex regions. It reduces to shortest path as regions become points. That's, I think, a key thing that we haven't broke it. The problem class is still NP hard. We haven't changed that. But we have either efficient branch and bound, or we have convex relaxations that are often tight. In particular, they're tight enough that with a little bit of rounding, we almost always get the optimal solution. I showed you this initial application in the manipulator planning at the dynamic limits. Okay, and I hope you'll give it a shot. So did we accomplish the deeper connections between these? This is, of course, just the beginning. But I do think that some of the combinatorial optimization, which looks so similar to the problems we were writing down in trajectory optimization, this is maybe just one of the obvious sort of connections that was waiting there for us to just write better. And I think that helps. I think it opens up what trajectory optimization, what we should expect out of our trajectory optimization. If you want more, the demo I ran was actually right in the course notes for my class. Nowadays, I rarely write an example if it's not in the course notes these days. So there's online class and lecture notes and everything inside that. And I'll stop by leaving the paper references up, and I wanted to leave some time for questions.
Great, we have a number of minutes for questions. So
I'll admit this is probably far too elementary a question for this presentation, but so you have this system of relaxation where you go from essentially Boolean variables to variables that are continuous between 0 and 1. And it seems to me like you've essentially gone from each of those variables having exactly 2 options to having uncountably infinitely many options. How is that easier?
Okay. I mean, it's about the convexity of the set. So if I have, if in a simple case, think about having a linear objective, okay, which says I want to be in some. I could go to the whiteboard, but I think it's really about having a continuous family. But it's a good continuous family where everything's connected and right. It's a convex set, and you have an objective which is pointing you in one direction, and so by the objective pushing you into some corner of that, let's say, of that bounding box, if there's multiples, it does make the problem easier, right? You can use standard algorithms, simplex algorithms to walk the corners or things like this. It actually does break some of that complexity.
Oh, so if you have something like n booleans, you can then model that as an n-dimensional hypercube.
That's right.
From 0 to 1, and then you can use something like any optimization algorithm like the ones you
I think that's exactly right. So think about the n-dimensional hypercube. Instead of having to visit every corner, I can think about the box and I can point myself in some direction and just find the closest. Yeah, that's a great.
Thank you very much. Excellent talk. 2 questions from my perspective. I'm a little older than the average audience. Visiting through convex sets, it's called the TSP with neighborhoods. And Mitchell worked on it for 10, 15 years with almost tight bounds. So it's my question number 1, what's the connection of your work with all the great algorithms to do TSP with neighborhoods with tight bounds? Second question, I might confuse you because it's completely unrelated. So my apologies. In optimal control, we have the notion of local optimality. If you found the globally optimal path, it is also optimal between any 2 via points. It seems much more powerful and natural approach than what you are trying to do. You are doing something strange. You are crossing obstacles. Wouldn't you prefer to start from the start using the notion of local optimality? I think it's also called dynamic programming or something, and get much more effective algorithms. I'm a little puzzled. So thank you.
Well, let me go back with you. So sorry, local optimality is simple. We get that from the nonlinear trajectory optimization. But it's insufficient. The locally optimal solutions are often far worse than the globally optimal solution.
But you search locally.
What's that?
You search locally, pieces by piece. I think it's called dynamic programming, I think.
We know dynamic programming. It depends how you parameterize your dynamic programming algorithm, right? A lot of them do not scale. I mean, sort of a nice dynamic programming algorithm on a mesh or something like this will tend to work very well up to maybe 5 or 6 dimensions if you're willing to compute. But we're trying to scale to much higher dimensions than that.
Gotcha.
And then the first one, so there are, I think, in fact, if you know any references that we might have missed, we did look carefully at all the TSP kind of algorithms, and I think they are not quite as general as this. There are places where those instances are very similar, and we try to compare. Okay. But I would actually, we should talk with you afterwards just to see if there's anything we've missed.
Okay.
Yeah.
Okay, thanks, Russ. That was a wonderful talk. I appreciate it. Especially like the interleaving of coding in the middle there. That was good. So it looked like at one point you were essentially building a volumetric representation or under approximation of the free part of the configuration space. I thought that was kind of hard to do. So how are you getting away with that? Is it because the particular models that you're using are somewhat simple in terms of geometric primitives, or what's going on there? I just kind of remember that as being difficult, but I've been away for a while. Maybe it got easy in the last decade or so.
So no, I think that's a fair question. So the question, I would say that what a PRM or an RRT is doing is also making a sample-based approximation of that free space, right? So anything you can do for PRM, I would say, let's just, every time I make a sample, spend extra time to come up with a local region. And we'd have the same sort of guarantees. It would probabilistically, we'd draw some sample that's outside of all of our regions, we would add a set, and we would expect in the same sort of probabilistic completeness kind of sense, we would eventually cover the space. We're not saying something stronger than that.
If you claim a volume, are you guaranteed that that's collision free, or are you not worried about that?
We have two versions. We have one that's very fast that doesn't make the guarantee, and we have a second version that absolutely makes that guarantee, but it has longer run times for it does scale to 14 dimensions, which is awesome, but it'll take an hour hours to certify potentially in 14 dimensions some of these. Right? Yeah. So, and you also mentioned in an earlier chat about growing balls, for instance, right? So if I were to just take my nearest neighbor collision queries and just try to grow the ball that fits inside the minimum distance to all the points, that can be too conservative. These are growing big convex regions by finding ellipsoids that are, they're polytopes that are pushed out by an inner ellipsoid. So they tend to be very big spaces. And like the shelf example, for instance, it just took 8 regions to get all the places we wanted to get on that. So I don't think it's gotten particularly easier. I mean, we do have some slightly stronger tools maybe, but I think it's worth the computation. You get a lot from a little bit of that extra pre-computation. Yes.
Thank you for the great talk. So I was thinking how we would get an approximation factor for the cases when the formulation is not tight. Could we exploit the structure of the problem or use primal dual approaches? Since the shortest path has a corresponding dual problem, we might also have a dual problem for this particular case with convex sets. So do you think developing such approximation algorithms is possible?
It's a great question. So we definitely understand the dual of the problem. Actually, it has some beautiful geometrical interpretations of what the dual can tell you. That in the simplest, shortest path problem, the dual solution, the dual variables for the flow constraints actually are the cost to go to on the graph. And there's a generalization of that we can see in the dual of this problem, which is like a small cost to go function. When the convex relaxation, the dual reveals like the cost to go structure on the sets, which is it's beautiful and good. The instances where the convex relaxation is not tight, we understand some of the properties of a graph that can cause that. Like the one that we use to do a reduction to NP hardness is when a bunch of cells are all overlapping and you can just walk around inside the cells without having to visit them. There's a couple of cases like that where things are perfectly in symmetry and you could really, but they're quirky examples. And so we understand those by having a handful of examples. I don't think we can say as much about them. I mean, we do have the primal dual solution. We can tell that there's an optimality gap, so we can identify when they happen, but we haven't thought more about, they seem quirky, and we haven't thought more about how to make those particularly better. Oh, sorry, I'll let the microphone people.
Okay. Yeah, so
oh, great.
Right so yeah, I have 2 questions. The first one is actually related to the last question. So you were mentioning that writing these constraints is difficult. So you mentioned that you missed some constraints and then Pablo was like, oh, you're missing a constraint. So I was wondering how difficult is it to write these constraints? If you come up with these convex regions, write the natural flow constraints, is that sufficient, or like are there things that like you got to be smart about how you're writing?
That's awesome. I'm super glad you asked that. So it is true that Pablo caught us and we had to add another constraint, but there's some sense in which though that I think you'd ask him, like, are you going to find another constraint? He'd say, no, we found them all. Like I mean, you can add generalization on the graph of convex sort of problem, but there's some sense in which we've kind of found them all, and that work is done. There's a chance you could make it better if you wanted to do something else, but that is carefully studied, well understood. Book is sort of closed. For the motion planning formulation, now we have this question of how do you encode trajectories in these sets? There's many decisions to make there. We made a particular set of decisions. I think that book is way open. We've got an initial version that was convinced us that this is important and impressive, but I think there's a lot more decisions about what constraints to add there. But once you cast it into the graph of convex, however you turned it into the graph of convex sets, then the machinery takes over, and that's pretty mature at this point.
So the kind of cases where you don't have this tightness, those are not due to, like right now, like the quirky cases you were mentioning for the last question, those are not due to like not having like the right constraints.
Correct. I think there is NP hardness. We will not have a convex relaxation that's tight in all cases. I think. I mean, you can add exponential numbers of constraints to get back up there, but if we limit the class of constraints, then this is, I think, the sweet spot of constraints that we've added.
And just another second quick question. So
Yeah,
you mentioned the dynamic obstacles case, and you mentioned you guys are working on that. Can you just tell us a little bit about like how you're approaching that case?
Yeah, of course. So, I mean, if I were to take a PRM that I do a lot of pre-computation, and then I would suddenly insert some obstacles, then you could imagine, you know, comparable to trimming edges that are now in collision, but leaving my graph around, I could shrink regions that are now in collision and continue to plan. There's a lot of things like that. I think a lot of the tricks that you would use in a roadmap, we could apply similar tricks here. There might be some things fundamentally better. We're taking some cracks at it, but that's the first thing I would try to do. Yeah.
So can you say a few things about how you represent the convex sets in the general configuration spaces, including non-Euclidean, and what kind of operations do you need online as post-containment in that set?
Yes, good. So, so in general, we want to find polytopes in Q, my joint angles. So Euclidean or non-Euclidean, I'm just going to write a polytopes, you know, linearly, you know, half plane parameterized polytopes in Q. For the sums of squares version, the sums of squares likes polynomials. Sines and cosines in Q are not as fun to deal with. There's a handful of ways you can transform those variables into polynomial coordinates. The one we did in the paper you'll hear on Friday, I hope, is by taking the stereographic projection. So you end up having polytopes in the tangent of Q, roughly space, tangent of Q over 2 kind of space. But it's basically polytopes in Q. And you're right that, well, so at runtime, the graph of convex sets parameterization does the work for you, right? So it's actually constraining the B-spline to live inside that polytope by putting convex constraints on the control points of the B-spline inside a polytope. Or any convex set, but inside the polytope. And so I think, what's the runtime concern in that regard?
Yeah, like what kind of operations then do you need during the online to interact with these elements? But the way I understand it, you have done all of the hard work, right? So now we can be naive users of the representation that you have built.
I hope you'll be, I hope some people will use it right out of the box. I hope some people will push it forward. But yeah, I think once you have the regions, which is an offline computation, the online computation really is just solving these convex problems. It should give you Q trajectories that you can just go and execute, right? If you have acceleration jerk constraints, those are coming soon, and effector constraints, we know how to approach that. Those are coming soon, but those are all, I think, can fit in the toolbox. Thank you. Yeah.
I think we'll have to unfortunately wrap it up there, but let's thank the speaker again. Okay, everybody, coffee break. Coffee is outside. We reconvene here at 11:15.
Sorry about the C-cell thing. No. It was just because I was like, what?
I had it written down, and then
it doesn't matter at all. No,
yeah.
That's great. Anyway, it's great.
Oh, sorry. What happens is, to make it complete, this axis is the design of the robots, using fields or whatever, and then this axis is the execution process. You add a wheel that doesn't do anything to the wheel that you want to apply. So you pay extra on the one dimension, but it's yeah.
So there's
You have permission. All of no matter what. So it's like a P norm. I mean, it's an infinity norm. So it's like a very high power. It's an extreme case. Zero value from it. Yeah. Should we grab some? Yeah.
Oh, thank you.
So are the speakers here?
Hey, good to see you. Good to see you.
Could they come and test it?
Yeah, let's work on the speaker.
Jason's gonna go before me, so Jason will be.
Just.
Oh, thank you.
Hey, everyone, come on back in and find a seat. It's time to get started with session 2. So before we start this session, I have 2 important announcements to make. First, perhaps most importantly, I want to let everybody know that additional coffee is on the way. So we'll let you know when that's available. Should be delivered here in the next few minutes. Second, I just wanted to call your attention to the program. If you notice, on Friday afternoon, right after the last talk, we've got a very, very short closing ceremony, which will include an awards presentation. We will be naming an outstanding paper award for the meeting, and I would encourage everybody to stick around to see how that turns out. Right. So very short, just after session 9 on Friday afternoon. Right. So those 2 announcements. I'm very happy to introduce the beginning of session 2. We turn it over to Lydia Tapia, who's the chair.
Jason. Super excited to be here for a WAFR in person after the pandemic. Let me go ahead and get our first speaker to set up. Hong Wei, are we set up? Great, perfect, thank you. So they're going to talk about distributed spacing control for multiple buoyancy controlled underwater robots. So go ahead and take it away, Kong.
Hello, my name is Kong Wei. I'm a postdoc associate working at here. This work, distributed spacing control for multiple buoyancy controlled underwater robots, is done with my advisor, Dr. Drake Paley. The research is the control part of our current work, which is finding a way for a distributed system to track and observe an underwater biology system named the scattering layer. Given the dynamics of the flow and the scattering layer, our distributed system can achieve desired formation while tracking the scattering layer by the derived control algorithm. Since it is an interdisciplinary work, let me first introduce the oceanography background and the platform we are using to explore the ocean, which is interesting. I will then talk about the distributed control algorithm in detail, which may not be that interesting. The scattering layer is a layer in the ocean consisting of a variety of marine animals. It can be seen to rise and fall each day in keeping with the Dell vertical migration. It is the largest ecosystem on the planet in terms of biomass, which is estimated to be between 5,000 and 10,000 million tons. Its Dell migration makes deep scattering layer play an important role in the pelagic food webs, serving as a vehicle for transferring energy between productive surface waters and the deep sea. Importance of a scattering layer in global carbon cycle is another reason that we need to investigate it continuously. Other motivation includes military purpose, since the scattering layer always appears as false seafloor from sonar. Traditional methods of detecting scattering layer achieved by tethered echo sonar or deploying trolling net. But the echo sonar can detect and observe only specific organism. Deploying trolling net, on the other hand, may cause troll avoidance behavior, which end up with underestimation of boil mass. Trolling net thus also disturb the behavior of the organisms in the scattering layer. In our research, DriftCam, which is a buoyancy-controlled underwater robot, is applied to perform the task. DriftCam is an untethered mid-water imaging system built to collect detailed information about the ocean animals by high-resolution video at the depth as deep as 700 meters. The DriftCam is equipped with LEDs, which provide the light for its cameras in deep ocean. The device is able to adjust its own buoyancy, pumping lighter than the seawater mineral oil to or out of an external bladder here, causing the DriftCam to move up and down in the water column. Its actions can be directed either by acoustic command or autonomously following a program preloaded in its inner computer. Quietly hanging in the water, drifting along with the water movement, the DriftCam collects video of the mid-ocean organisms, such as those in the scattering layer, with minimum disturbance. So the last picture is a diving experiment done in the neutral buoyancy water tank in the University of Maryland. This video is taken by Rachel Suter, PhD student from the University of Maryland during a cruise in the Gulf of Mexico. So see, look at the the DriftCam. So look at those sea creatures and the robots hanging, flowing in harmony. Okay, so consider. So now it's the boring part. Okay, considering the physical scale and the motion style of the scattering layer, it is reasonable to deploy a multi-agent network of DriftCam for this task. So the optical cameras have limited perception range, especially in the ocean. Communication range between those DriftCam also has a limitation. A swarm can cover a large-scale space, such as the scattering layer, and it is also tolerant of individual or partial network failure. Given the ocean flow field and the dynamics of the scattering layer in the horizontal and the vertical axis, our goal is to have any DriftCam achieve equal distancing D with its immediate neighbors and tracking the depth of the scattering layer. For simplicity, the flow field is modeled as a shear flow, and the depth dynamics of the scattering layer is considered as a harmonic oscillator. For full depth water column, the flow velocity field can be approximated by the combination of shear flows with varied slopes. The control input hinges on the difference between the drag force and the buoyancy. Both the DriftCam and the scattering layer bear the flow velocity in the horizontal direction. One technique that we apply is the backstepping method. It is basically designing the control force based on the result of W, which denotes the desired vertical velocity for control objective. What I'm trying to say is that once we have known what W looks like, we can then use the backstepping method to derive U here. So now let us pay attention to W, which has two tasks. One is to have equal distancing, and the other is to realize the depth tracking. We first pick a potential constructed on the sigma norm of horizontal distancing, a distance between those DriftCams. This norm is used to make zero differentiable. Then we can later prove the gradient of the potential is very key in realizing distancing control for those drift cams. At last, the tracking is achieved by a feedback controller, given the information of the depth and the vertical velocity of the scattering layer. Because of the time limitation, I just briefly introduced the proof. We first transferred the dynamics of the drift cam swarm to a new coordinate centered as its mass center. We can show that the potential does not change for this transformation. With the coordinate transformation, the task of depth tracking is divided into 2 steps. The first is achieving depth consensus for the swarm, and the second is depth tracking for the swarm mass center and the scattering layer. At the same time, we can see the gradient of the potential guarantees the network of agents converge to the global minimum of the desired configuration. This can be proved by picking a Lyapunov function candidate, applying Lascelles invariance principle. The potential function is deliberately selected, so there is no local minimum. Once we have the desired vertical velocity for the control objective, we can design the force controller by backstepping method. Here is the simulation result. 10 drift cams are released, and we can see they achieve equal distancing and depth tracking at last. The time of the process depends on the horizontal flow velocity. Actually, we can achieve different configurations given the requirement of the task. We are currently trying to design a flow estimator through estimating the relative motion with their neighbors within each drift cam's perception range. Meanwhile, our final goal is to observe the motion of the scattering layer, which can be quantified as the density field of the ocean organisms. We are now using ensemble common filter to estimate the density evolution within the scattering layer. The control part result provides a new perspective on taking advantage of the environmental flow fields to facilitate formation control from the long-endurance multi-agent system with a limited onboard actuation and capability. Our research can be applied to monitoring other large-scale ocean ecosystems and can potentially be used as a method to detect other underwater vehicles. But for a very large swarm to be released, say 1,000 drift cams, to achieve a desired formation may take a very long time. For example, for a configuration of horizontal line using our algorithm, it may take days depending on the initial formations. At the same time, to observe or monitor a specific underwater phenomenon, an optimal formation considering such as the formation time and coverage requirement is to be designed. Thank you.
So we are holding questions at the end. So please, if you have questions, please hold on to that because we will take those all at the end. Our next speaker is going to set up and I'll give him a second while he's setting up. So our next speaker is Max Haushager, and you knew it was going to happen. He actually tested before just to make sure that something would go wrong during. So as he's getting set up, he's working at Neuro, and we're really excited. Yeah, exactly. I can keep talking for a while. So I was telling the co-chairs, the coffee during the break is not, you learn from these things during WAFR and you adapt. I remember in WAFR 2 years ago, I was yelling at the lady serving, or 4 years ago, 2 wafers ago, serving the cake to please just put it out on the table so people would take them to go, because we had to speed up the lunch service. So yeah, all these things, they get figured out. And so we are good to go.
Perfect.
Max is gonna talk to us about lane level route planning for autonomous vehicles. Go ahead and take it away, Max. Thank you.
Picking up? Yeah, it is. Perfect. All right. Hi, I'm Max. I work at Neuro. We're an autonomous vehicle company, and we're specifically focusing on last mile delivery. We build our own hardware. You can see one of our bots on the slide, as well as the software that drives these unmanned vehicles. What I want to talk to you about today is our routing algorithm. That is the piece of software that determines which roads and specifically which lanes the vehicle should take on its way to its destination. And I want to start with an example. Let's say I'm ordering food for delivery from just down the road. So now an autonomous vehicle needs to make its way from the start point S to the goal point G, where I'll be waiting for my food. Google Maps makes this sort of route planning very easy for road level route planning. It'll determine which roads I should follow, and a human could easily follow this route because a human can make up their own mind which lanes to take and when to change lanes if a lane change is necessary. But this also means that this sort of road level route planning isn't sufficient for autonomous vehicles, because an autonomous vehicle also needs to be able to make those decisions of when to change lanes. So really what we need is a route planner that reasons in lane level detail. Here's the exact same map, but this time all the lanes are individually marked as green lines. And you can see that this main road that we're starting out on has 4 lanes, 2 lanes going one direction and 2 lanes going the other direction. Here's the Google Maps route superimposed on that. And I want to zoom in on this intersection where we will be making our left turn. And you can see that if we start out in the rightmost lane, at some point, we're going to have to lane change into the left lane so that we can turn into the road where our goal lies. But of course, you can't always just change lanes whenever you want to. You need to watch for traffic in the target lane, and you need to find a gap that you can merge into if there is traffic. And what that means is that if you leave it too late, there's always the risk of me not being able to lane change in time and missing my turn. So the question this poses is, what is the optimal time for me to start attempting to lane change? I don't want to leave it too late because then I risk missing my turn. But also I like driving on the right-hand side as much as I can, so I don't want to lane change too early. But maybe the risk of missing the turn is actually too high. Maybe traffic is heavy. What if there's an alternative? Maybe we make a right-hand turn before that intersection, and then after 2 more left-hand turns, we get to our goal entirely without any lane changes at all. The trade-off we've made here is that we travel a little bit further and we have to perform an extra unprotected left-hand turn. But what if taking the risk of missing the turn actually isn't too bad? Let's say we can risk failing the lane change and missing the turn because we can simply just take a right-hand turn after the intersection, and after 2 more right-hand turns, we get to our goal position without any lane changes and without any unprotected left-hand turns. So what should we try to do here? We've talked about these 3 different routes and some of the considerations you might want to make in deciding. And in general, this really isn't an easy problem to solve. We could cook up some heuristics that will give us a workable solution, but really what we're after is a unified mathematical framework that lets us find an optimal solution and do so computationally efficiently. So let's start super simple. With this 3-lane road, we have a merge lane on the right and an exit lane on the left. And the first thing we'll want to do is we'll want to discretize those lanes into individual cells with cell boundaries in between them. And once we've done this, we can connect them with their neighbor relationships. So each cell can have at most 1 left and 1 right neighbor, and each cell can have 1 or more predecessors and 1 or more successors. And what this gives us is a directed graph representing the lanes in this road, suggesting that maybe we might be able to use some graph search methods on this. And this is what this looks like in practice. All these colored rectangles here are individual cells, and multiple successive cells make up each lane. And you can also see that in general, the graph we get this way contains cycles. But of course, we still have a problem. Just because two cells are neighbors and have this directed edge between them doesn't mean that we necessarily can traverse that edge, that is to perform a lane change. If there is traffic in the target lane, we may not be able to. So what this means is if we attempt a lane change, we may end up in the neighbor, but we might also end up in the successive node, and we don't know that ahead of time. So what we really need is we need a stochastic model of lane changes. And it turns out that the probability of lane change success tends to depend on the distance we have available to perform that lane change. So what we want is we want a function f that maps from the length of each cell to the probability of lane change success. And this function f should have a few properties. The first one being that on a zero length cell, we have zero probability of lane change success. On an infinitely long cell, lane change success should be guaranteed. And on two successive cells of length L1 and L2, the probability should be such that it's the probability of failure of success on the first cell of length L1 plus the probability of failure in the cell of length L1 times the probability of success in the cell of L2. And it turns out there's only a single function that satisfies all these constraints. And I'm sure many of you will recognize this as the cumulative density function of a exponential distribution with this rate parameter alpha. And this rate parameter has a nice physical interpretation in that it's the number of lane changes we expect to be able to do per unit length. Or in other words, 1 over alpha is the expected distance traveled between first deciding that I'd like to lane change and actually completing the lane change. And of course, this alpha is a tunable parameter, so it can depend on traffic conditions or perhaps the capabilities of my software stack. I can tune that as needed. So now that we have that out of the way, we'd like to define a Markov decision process. And for a Markov decision process, we need some actions. So let's assume that I'm currently traversing a cell X. The simplest thing I can do is I can stay in lane. And staying in lane has a success probability of 1. And we define a cost C of X of traversing the cell X that we incur. We can also attempt a lane change, which can either succeed or fail. The success probability is defined by this function f that we just talked about. And if we do lane change, then we incur not only the cost for traversing the cell X, but also an additional lane change cost that is meant to discourage us from performing unnecessary lane changes. If we fail the lane change, we only incur the cost for traversing the cell X. And then finally, we also have a forced lane change action, which again has a probability of success of 1, but we incur not only the cost of traversing the cell and the lane change cost, we also incur this additional forced lane change cost times the probability that the lane change would have failed otherwise. So now that we have the lane graph and these actions, we can define a stochastic shortest path problem. That is, what is the path that minimizes the expected cost towards our goal? And in general, for general MDPs, we could use algorithms such as policy or value iteration. The problem is that those are at least quadratic in the number of nodes, and in this case, the number of cells. And for very large MDPs, that becomes computationally intractable. And we are trying to route across entire cities. So ideally, we'd like to use some sort of graph search method that is less computationally complex. And specifically, we'd like to use something like Dijkstra's algorithm that finds the shortest path by computing all the optimal costs to go from all the nodes, where the optimal cost to go at a node is the length of the shortest path from that node to the goal. The applicability of Dijkstra's is conditioned on the property that all edge weights have to be non-negative. That is, I can't decrease my cost by traversing an edge. In other words, what this means is that the optimal cost to go at a node X must be greater than or equal to the cost to go at a node X dash if the shortest path takes me from X to X dash, or if X comes before X dash in the shortest path. This is also called the monotonicity requirement for Dijkstra's algorithm. In our case, we have stochastic actions, so monotonicity looks a little bit different, but it's the same idea. The optimal cost to go at a cell X must be greater than the optimal cost to go at a cell X dash if we have a non-zero probability of reaching X dash from X when following the optimal policy pi of X. And this is the central insight of our work, is that if our cost formulation is monotone, then we can apply a Dijkstra's-like algorithm that solves this lane level routing problem in a single pass. And it turns out that there is a very mild condition for monotonicity to hold. I won't go to the proof here, but of course you can find it in the paper. The condition is simply that the forced lane change cost must be less than or equal to the cost of the cell divided by rate parameter alpha times the length of the cell. To give you a physical idea of what that means, let's say we use the length of the cell as the basis for cost. So let's just simply set C of X is equal to L of X. In this case, you'll see that the forced lane change cost needs to be less than or equal to 1 over alpha, which we've already talked about is the expected distance traveled between first attempting to lane change and actually completing the lane change. The other thing that's interesting about this is that we can vary this. This only has to hold locally for each cell individually. So what that means is that we could, for example, for some roads, vary alpha because lane changes might be more difficult because those roads are faster traffic or more traffic than for other roads, or maybe it's easier to lane change at midnight than it is during rush hour. As long as this condition holds locally for each cell individually, a cost function is monotone, and our Dijkstra's-like algorithm will work. This is where the dirty laundry comes in. Because of monotonicity, there is also a limitation on the expressiveness of the policies that we are able to obtain. Specifically, you'll never get a policy that allows for cycles. So in this case, where if we wanted to lane change from the right into the left lane and we missed it and went around, the policy won't allow us to do that. The policy will have a forced lane change before the loop. In practice, this doesn't tend to matter all that much, but this is the price we pay for the computational efficiency of Dijkstra's. So let's apply our algorithm now to the example from the beginning. So what I've done here is I've colored all the cells in this lane graph according to the optimal policy. And specifically, a green cell means stay in lane is optimal. A yellow cell means change lanes is optimal, and the hatch pattern tells you in which direction the policy wants us to lane change. And the red cell means a forced lane change is optimal, and again, the hatch pattern tells you in which direction. So in this case, you can see that starting from point S, the policy has us continue along the rightmost lane for a while, but then quite far away from the intersection where we need to left turn, it tells us we need to start thinking about lane changes. We can also get some really nice emergent behavior out of this router with very simple cost adaptations. If you're driving on a high-speed road and there is a merge lane coming up, a good driver will often go into the left lane to prevent having to brake hard for someone that might merge in front of you. So what we've done here is we've added a cost on traversing any cell that has more than one predecessor, so basically the cell that comes right after the merge. And what you can see is that the policy is having us lane change out of the rightmost lane just before the merge, and then after the merge, it has us lane change back into the right lane to reach our target at G. And then for my final slide, I want to leave you with this video of the router routing across the entirety of Houston. I've had to slow this down by 50 times right roundabout to make it visible what's happening here. As you can nicely see the fronts of the algorithm expanding. This took somewhere between 150 and 200 milliseconds on a work desktop. So this is very much applicable to real-time autonomous vehicle routing. And with that, I want to thank you for your attention, and I'm looking forward to your questions. Thank you.
Thanks, that was great, Max. Have our next speaker come to set up.
Trying to steal your microphone.
No, we're good. So go ahead and get your, do you want to just hold it or you want to, whatever is easiest for you.
I'll just hold it.
Great. So our next speaker is Saurav Agrawal. He's from UNC Charlotte, and he's going to talk about his paper on the correlated arc orienteering problem. Thank you. Go ahead and take it away.
Hello, everyone. Our paper is titled The Correlated Arc Orienteering Problem, and it is co-authored with Srinivasa Kela. So let's first look at the orienteering problem. In an orienteering problem, we are given a graph G with a vertex set V and an edge set E. We have rewards on the vertices V, and we have cost on the edges E. And we are given a robot with a finite budget. The task is to find a tour or a path such that the sum of the cost for the tour is within the budget. And we need to visit a subset of the vertices such that the total reward collected is maximized. The team orienteering problem is a generalization of the orienteering problem with k-robots. Next, we'll look at the arc orienteering problem, wherein again we are given a graph G. However, over here, the rewards are on the edges instead of on the vertices. We have cost on the edges, and we are given a robot with a finite budget. And here the task is again to find a tour such that the sum of the cost is within the budget. However, we are visiting a subset of the edges instead of a subset of the vertices in the orienteering problem. And we want to maximize the total reward that is collected from the edges. The team orienteering arc routing problem is generalization to k-robots. You et al. Gave a generalization of the team orienteering problem, which is known as the correlated orienteering problem. Over here, the rewards are correlated. What this means is that visiting a vertex can provide information associated with a correlated vertex. And it is defined by weights, which gives a fraction of the reward associated with a vertex V that can be collected by visiting another vertex V prime. They gave a mixed integer quadratic program formulation for the problem. In this paper, we introduce a new problem called the correlated arc orienteering problem, where the rewards are associated with the edges, and they are also correlated with each other. So this means that visiting an edge can provide information associated with the correlated edge. And these correlations are defined by a weight function, which takes in a pair of edges and gives a fraction of the reward associated with an edge E, collected by servicing another edge E prime. So this problem is a generalization of the team orienteering arc routing problem, as TOARP does not consider correlations, and we are considering correlations between the rewards. It is also a generalization of the correlated orienteering problem. So we can model rewards on the vertices by treating those vertices as degenerate edges. And so we can model both vertices and edges in the same framework. So hence it is a generalization of the correlated orienteering problem as well. So let's look at a simple example. Over here, we have a spiral pattern composed of 77 line segments, each of unit length. We assign a reward of 1 for each segment. And we have correlations based on the field of view. So over here, the blue box shows a field of view such that traversing an edge can observe immediately parallel edges. So here are the solutions using an AOP formulation on the left and CAOP formulation on the right. The AOP tool covers 53 segments, whereas the COP optimal tool covers 69 segments. So we can see that COP is able to exploit correlations to generate more exploratory solutions. So using this idea, we were able to also apply it to coverage of road networks, where we are given an input urban road network, and then we are given a team of robots. And the COP formulation can utilize the field of view to generate efficient routes that cover as much as the road network as possible. So let's formally describe the correlated arc-orienting problem, which we do by formulating it as an MIQP. So we are given a graph. We model the environment as a graph, which is undirected and connected. We also have depot locations in the graph from where the robots start and end their tours. We are given K robots with individual capacities Q for a robot K. A unique characteristic of our formulation is that we have two modes of travel, servicing and deadheading. When a robot take actions such as taking images, then we say it's servicing and there is a cost associated with it. And when a robot is transiting from one vertex to another, then we say it is deadheading and there is a cost function associated with it. We have servicing variables that are binary, and we enforce that each edge can be serviced at most once. We have deadheading variables that are non-negative integers. So this means that any edge can be deadheaded as many times as required. And the task is to compute a set of routes. So now we can formulate the capacity constraints for the robot. So the total cost of a route is given by the summation of the service cost plus the deadheading cost for the edges that are being traversed in the route. And this cost should be less than the given capacity of the robot. So now let's look at the rewards and the correlations. The reward function is a non-negative real for the edges. And we have special correlations that are modeled using the weight functions. For a pair of edges, it gives a non-negative real value. And these represent fraction of the reward RE for an edge E that would be collected by traversing another edge E prime. We define a set of neighbors NE, which corresponds to the set of edges that can observe another edge E. So when we service an edge, then we collect a reward equal to R of E. However, when we do not service an edge, then we can collect a reward through correlations by visiting the neighbors. And this gives us the expression for the total reward, which is a combination of the above two cases. And this is quadratic because we have two variables being multiplied. So now we can give the MIQP formulation where the objective is maximization of the total reward. We also have total cost term, which helps in optimizing when the budget is very large. We have constraints that for servicing, which says that we need to visit each edge at most once. We have sum of weights as the constraints. We have capacity constraints, and then we also have routing constraints, which ensures that the each individual route is connected to the respective depot. And then we have variable bounds. So now the COP problem is NP hard, and solving the MIQP to optimality can take a very long time. And thus we develop new heuristic algorithm for computing routes rapidly. There are three important steps that are performed iteratively in the algorithm. First step is to maintain a set of visible routes. Then we greedily select an edge that needs to be added to a route, and then efficiently construct a new route by adding the selected edge. We have an additional compute route heuristic, which is a constructive edge insertion heuristic that runs in linear time. And this helps in bounding the overall complexity of the algorithm, which is O of M cubed, where M is the number of edges that have positive rewards. So we have the reward function and the spatial correlation, which was given by the weight function. We defined the set of neighbors, which were corresponding to the edges that can observe an edge E. We now also need to define co-neighbors that are the edges that an edge E can observe. And this gives us the definition of utility of an edge, which is the reward associated with the edge plus the total sum of the rewards it could receive through correlations. And then we have the greedy selection criteria, which is the difference in the scale utility and incremental cost of adding an edge. With this as the greedy selection criteria, we select edges. And then once we have incorporated it into a route, we update the scaling factor and the utilities. So we applied COP to an environment monitoring problem where we wanted to estimate the methane gas leak rate from oil wells. And these oil wells are shown as blue dots in these figures. And we're using a ground robot to find routes on a road network. We model the rewards as expected entropy reduction. And the correlation weight function is developed using expected square distance between the edges. So we compare the greedy algorithm with the MIQP solution for a data set of 100 road networks from the Permian Basin in Texas. And we could obtain solutions within 8 milliseconds for each of the environments. And on average, the greedy solutions were within 9% of the optimal MIQP solutions. So to summarize, in this paper, we introduced a new problem, the correlated arc orienting problem, that considers correlated rewards on vertices and also on edges. The formulation is a generalization of the team orienting arc routing problem and the correlated orienting problem. We developed MIQP formulation to obtain optimal solutions. We developed a greedy algorithm that runs in O of M cube time. And these algorithms and the formulations are applicable to both TOARP and COP. We showed applications to coverage of linear infrastructure, such as road network, and for environment monitoring. So let's look at the dirty laundry. We performed empirical evaluation of the greedy algorithm, but we do not have any theoretical guarantee. We can find better methods to represent the information for environment monitoring by developing new methods for modeling of rewards and weight functions. Future work includes cleaning up the dirty laundry by developing approximation algorithm, and developing new methods to formulate reward and weights, particularly for environment monitoring. We also are interested in looking at higher order correlations because right now we just considered quadratic correlations. And also we are interested in online version of the problem. Thank you.
Thank you. Are you good? Do you want to clip it on or you want to hold it?
Yeah, that's okay.
Our next speaker is Xiaoming Jing. He's going to talk about He's going to talk about glide, generalizable quadrupedal locomotion in diverse environments with a centroidal model. Go ahead and take it away.
Okay, so hi everyone. So today I will present our paper, and this work is a collaboration between all these wonderful institutions. Okay, so before I go into the details, let me first give you an overview of reinforcement learning for locomotion control. So in reinforcement learning, we try to learn a policy pi. And in this case, we usually parameterize them by a neural network. And the input to a policy is the state of the robot that we want to control. And the output of the policy is the action that the robot will take to interact with the environment. And the goal, and in addition, the robot will also provide a reward to the policy as feedback. And the goal of reinforcement learning is to maximize the sum of rewards over some time horizon. So there are several challenges of applying reinforcement learning to real robots. So first of all, as our robot gets more complex, so we have a lot of degree of freedom on the robots. So we need to collect a lot of samples in order to get enough data to train the policy. So it's only feasible to collect those data in simulation. Otherwise, you can easily break your robot. This leads to the second challenge, the sim-to-real challenge. So all simulations are wrong, and mostly when you collect data in simulation, the policy usually doesn't just directly work on the real robots. So people spend a lot of time to tune their simulation model so that it's more accurate, and even that is not enough, and you need to do some randomization in simulation so that your policy is robust to this sim-to-real gap. And finally, we have the challenge of reward design. We need to tune our reward really carefully in order to get the behavior that we want on the real robot. So a lot of the existing work out there is what I will call full model reinforcement learning, in which case they will build a very detailed full order model of your robot in simulation, and then they will do Monte Carlo rollout in this simulation to collect data to train the policy. And if you are not careful with your reward design, you can get some really funny behavior on your robot. So here, the reward is just to check a desired velocity for the robot. And actually, this policy achieves perfect reward in terms of checking the desired velocity, but clearly, nobody will want to put that motion on a robot. And the solution seems to be reward engineering. So if you look at papers that actually come up with a system that can generate policies that work on the real robot, and you look at their papers, usually they dedicate a whole page of their paper just to describe the reward function. And even if you tune your reward function carefully and you generate a capable policy, because you build a very detailed model of your robot, so this policy will only work on this particular robot. And if you make small modification to your robot, in this example, we invert the knee of the hind neck of the robot, and the policy wouldn't work, and you need to train everything from scratch again. But wait a minute, model-based community tells us that a table model is all you need. You don't need a full order model to come up with a capable policy. So why don't we just use that to train our reinforcement learning on this model to train our policy? And so first, let me define the centroidal model that we use. So in the centroidal model, the robot is objected as a single rigid body model. So with 4 massless legs attached. So first we made the following assumption. The context sequence is pre-specified. So we know the robot is either doing trotting, pacing, or walking gait. And this allows, so this means that at each moment in time, we know exactly which set of legs is in stance phase and which set of legs is in swing phase. This allows us to divide the controller into 2 controllers, the stance foot controller and the swing foot controller. So for the stance foot controller, the input to the policy will be the state of the rigid body, and the output of the policy is the desired acceleration of the rigid body, meaning the linear acceleration and the angular acceleration of the rigid body. And because the system is under-actuated, we cannot just generate any desired acceleration we want. This will go into a QP solver that generates a set of ground reaction forces for the stance foot, so that it can generate a acceleration that's as close to the desired acceleration as possible. For the swing foot control, the input to the swing foot controller is also the state of the rigid body. This will go into a foot placement strategy. In this case, we are just using a simple Rebel heuristic, and the output is a desired position of the swing foot. Now, with this centroidal model well-defined, we can now do Monte Carlo rollout using this model. And the advantage of using this centroidal model instead of a full order model is that it's faster to simulate and easily parallelized so that we can collect data real fast. And also, we only need to regularize the behavior of a single rigid body instead of worrying all the degree of freedom that you need to worry about on the full order model. But it also comes with disadvantage. For example, it doesn't know the notion of drawing or torque limits. So if your task requires the robot to operate on those limits, then it probably will fail. And then we also assume a fixed gate timing. So it's always doing this trotting gate or pacing gate, and depends on your task, it might not be optimal. But in our scenario, we find this advantage is not a problem. And eventually, we want the policy that work on this simplified model to transfer to the full order model. But that's pretty simple. We can just do Jacobian transpose for the stance legs to transform ground reaction forces to joint torques. And then we do position control for the swing legs. One good thing about the centroidal model is that once we train the centroidal model on a simplified policy on the centroidal model, it can generalize to different configuration of the robot legs. And we can also efficiently train policies to try to tackle this challenging stepping stone terrain. So the policy is trained on the centroidal model and can directly deploy on the full order model in simulation. And we also have this example of asking the policy to cross this balance beam. And finally, we also have an example of a two-legged balancing problem, which you can consider that as a more complicated acrobat. And of course, we want the policy to also work on the real robot, but that's pretty straightforward. The centroidal model doesn't care whether your full order model is in simulation or a real robot. In this case, the same policy can work on simulation and, sorry. And directly deploy on the real robot. It's pretty robust to unknown terrain, so we just put some obstacles on the floor and the policy can handle it pretty well, even though it's trained on a very abstract centroidal model. We don't have a perception system required to do a full stepping stone test on real robot, but we come up with this proxy test. So it's just asking the robot to cross this gap. So let me also briefly give you an overview of what we are working on now. So you remember the limitation of this model is that it assumes contact sequence is pre-specified, and we also have this foot placement strategy that needs to be tuned. So maybe if we can also learn the contact sequence, so like a policy to decide whether one foot should be in swing phase or stance phase, and also use a policy to decide where we should put our foot, we can get better policy. So here is a table of comparison. So in the first column is a heuristic where everything is not learned, including the body acceleration, which is tuned with a PD controller to track a desired velocity. And it works pretty well on continuous terrain, as been shown by many work in model-based control literature. No matter how hard we try to tune the controller, we find that it is hard to make it cross this challenging stepping stone scenario. But with our glide framework, so we have a policy to learn the desired acceleration, then we can generate a very stable walk across this stepping stone terrain. However, because the contact sequence is pre-specified, so it's always doing this trotting behavior, no matter what command velocity we use. So for example, when we command the velocity to be 0, we want the robot to be standing still in order to be optimal in terms of energy efficiency. So we have another policy that also learn the contact sequence. So a policy decide whether a foot should be in stance phase and in swing phase. And now, and now we get a behavior where when the command velocity is 0, it will do the standing gait. And when we ask it to walk forward, then it will directly use the trotting gait automatically. We also train a policy to cross this long gap terrain where you can see it could be pretty challenging to use a trotting gait to tackle this terrain, but our policy learns some sort of galloping gait, I think, to cross the terrain. And as we replace more components with learning-based components, it gets better and better. And we are still in the progress of replacing the food placement strategy with the learn components. And hopefully after that, we can get the best performance. So to summarize, we find that reduced order model can be effective for reinforcement learning, and integrate model-based controller can simplify design process. So now go to the dirty laundry part. So the question now I ask myself is, do we really need to use this simplified model? So why do I ask myself that? So first of all, the robots are getting better. Even bad motions can work on the hardware. So if you look at some of the recent work that use reinforcement learning to train policies for quadrupedal robot, their motion is really, really bad. But it works on the hardware because our robot is just getting better. So maybe it doesn't matter whether we have good motion quality or bad motion. And if you remember in our pipeline, we have a Qt solver that makes the whole process kind of slow compared to just using a full order model and then just do draw and talk control. So the benefit of using a simplified model become less obvious. And finally, simulations of full order model are just getting faster and faster. So, and nowadays machine learning people say that data is all you need. So if you just simulate long enough, you can get capable policy. Yeah, so that's all. Thank you.
Thank you. I'll welcome the 4 speakers back up to the stage so we can start our question and answering session. So just remind you, if you have a question, we've got mic runners and we need to use the mics for the online presence as well. Great. Let me go ahead and take it. Good question.
So to Maximilian, so you have your lane level route planning, and it accounts for things like you mentioned lane changes and forced lane changes, which I presume would be things like the space might be a little tight, but we're going to switch into that lane anyway because we don't have a choice. And you tried to penalize that. And so you get what I'll call what I think is a static route plan so that you can get from one location to another location. What if things dynamically change, like a lane closes or there's a collision or ducks are crossing the street and now your plan no longer holds and you can't even do a forced lane change? It's just not open. Then what happens?
Yeah, so the policy is static in the sense of you compute it once for a goal and then it covers the entire area that you might be driving in, but it doesn't necessarily prescribe, right? It takes into account to an extent the stochasticity of, I might not be able to do a lane change. So if for some reason I don't get to lane change, that is baked into the policy. What wouldn't be baked in is, yes, if something changes on a more fundamental level, so like you said, for example, a road completely closes or something to that extent, then you would have to run the routing algorithm again with that new information of actually this road is closed. But in terms of does a dog cross the road or is there traffic around us? That problem is more low level and is handed off to whatever motion planning framework is driving your car. And the router tries to take into account those variabilities, at least with respect to lane changes. And that is why that stochasticity is baked into the router formulation and ultimately the policy.
Yeah. Any other questions for our speakers? Thanks.
I have a question for Kong. Very nice work. Thank you for your presentation. I was wondering, you mentioned that those driftcams will communicate with acoustic transponders, right? So given that acoustic signals have very limited communication bandwidth, have you thought that you may have some problems with acoustic communications? And if yes, because this is going to be a decentralized method, what are the communication requirements for your methodology to work?
Let me rephrase it to see if I understand the question. So are you asking about the requirement of the communication?
There are basically two questions. The first question is, what are the communication requirements? And if they are heavy or like high, how do you plan to address that problem, given that acoustic communications have very limited bandwidth?
Okay. The communication requirement now depends on the task. So basically, because the control is only a part of our research, and another very important thing is how can they estimate the flow field, the environment. And to do that, they just need to, because the drift cam, they just drifted with the flow horizontally. So what they need is they need to detect the motion of at least their immediate neighbors. So that is not an active communication. It's kind of a passive. And other than that, if you have the estimation of the flow and you have control, then what you need to do depends on your goal. For example, here we want to observe the motion of the scattering layer. So then I think we, to capture the density of organisms, we need at least some reciprocal communication. So that depends on the task. Yeah.
Cool. Thank you.
Mm-hmm.
Do we have any other questions? Great. I was looking for the other side of the room, so the mic runner up that side.
There's a question for Saurav. You said that you had no theoretical guarantees of your performance for the greedy algorithm. Is your objective function in that problem, have you checked if it's submodular at all?
So we do not make an assumption that the objective function needs to be submodular, but for specific kinds of function, for reward functions, it might so happen that the objective function is submodular, and in those cases, it might be easier to prove a guarantee, but we haven't worked on that yet. I'm aware of approximation algorithms for submodular functions, but over here in the formulation, we do not make any assumption as such for the rewards.
Yeah, go ahead.
Very quickly, you said you proposed the NemIQP formulation. Was the cost quadratic and convex or not convex?
Sorry, I didn't catch the question.
You said you proposed the NemIQP formulation for the problem?
Yes.
Right? Was the cost convex or not convex? Just to understand.
So I'm not sure if the cost is convex or not. It's definitely quadratic, but that's something that we need to analyze whether there's convexity in the function or not.
Okay, thank you. Thank you very much.
Can you raise your hand again? Perfect.
Hi, I have a question for Zhao Ming. Thank you for your talk. So when you train the reinforcement learning algorithm on a simplified model, what are the details involved in transferring that policy to a more complicated robot? Because that seemed to be a really important step.
Yes.
So yeah.
Yes. So as I mentioned in the presentation, so the policy in the central model will eventually give us the ground reaction forces for the stance foot. And you can transform that into joint torques for the stance foot using Jacobian transpose. And then for the swing foot, we have the central model give us the desired position of the swing foot. And then we can come up with like a Bezier curve connecting the current foot position to the desired foot position and then do position checking for the swing foot. Does that answer the question?
Yep. Thank you.
Thank you.
Yeah, I had a question on the lane change paper. Yeah. So you presented like 3 properties that you wanted of the density function, right? I definitely understood the first 2, but in the third one, you were saying essentially on a lane of length L1 plus L2, you had like failure on L1 and then success on L2. But that seemed to be like you're assuming some independence on those 2 segments, which maybe doesn't really model the true system. Isn't that true? Like, I'm just thinking if you're driving and there's a car driving beside you and you fail in a lane change, then if you try again a little bit later and the car is still beside you, you know, they're correlated events.
Right. I'm actually super happy you asked this because there was a point that I just realized I forgot to mention in the presentation. The reason for that constraint is that we would like the model to be independent of whatever the size of the cell that we subdivided in. So if we subdivide smaller, then we don't want the model to change. But yes, that's a good point. I wonder if that, I'm not 100% sure. I'd have to think about it, but that's a good point. We do assume them to be independent. I'm not sure if that actually changes much. But yeah, the reason for that particular constraint is so that our model of lane change success is independent of whatever size we subdivide the cells in. I guess you could do something where it's not quite that function. It's something that is basically, if I failed previously, then I'm more likely to also fail in the future. You could probably come up with a function that does that. But at that point, I guess you're tuning, right? You also need to determine, well, how correlated are these things? But it's an interesting idea. I haven't thought about that.
Okay, thank you.
Any other questions? Great.
Yeah, I want to ask Jiao Ming. So yeah, I want to know more about what is the state in the agent. I'm pretty sure that it's not images, but I don't know what you use to train the agent because like as human, I kind of need to see the whole road ahead, you know, to kind of plan where to put the foot in or something like that. So I don't know, like if you have, you can describe the state in the agent.
Okay,
So
can you repeat the question? I didn't quite catch that. Sorry.
Sorry?
Can you repeat the question?
Yeah, I want to know more about what is the state in the agent. Like what kind of thing that you use to be the state for training the agent?
So you mean the input to the policy?
Yeah.
Yes. So the input to the policy will be the state of the rigid body. This means the linear position, linear velocity, orientation, and angular velocity of the rigid body. We also know the foot position with respect to the rigid body. So like where the foot is currently as input to the policy.
But I mean, how can the agent kind of knows where to put the foot on? Because like if a human kind of walk in a uneven surface, right? We kind of need to kind of see the surface.
Oh,
like,
you mean the terrain? Okay. Yes.
Yeah.
So for the terrain, we have a height map on the terrain. So I believe it's 1 by 1 height map around the center of the robot, and it's only used for swing foot control. So for example, for the stepping stone terrain, first we use the Weber heuristic to decide where we should put our foot. But for example, in the stepping stone terrain, not all footholds are feasible. If the Weber heuristic, we choose a foothold that's not feasible, then we will choose the closest point on feasible terrain. So we will choose a point on the feasible terrain that is closest to the Weber heuristic, and then we will choose that as the foothold. But for the standstill control, we didn't consider the terrain. So we just know where the foot is with respect to our body. Yeah. Great.
Great. Did that answer your question? Thanks. I think we have a question over here.
Oh, this question is also for you, Xiaoming. I didn't completely understand why does the centroidal model made reward design simpler? So how does this work? And what is your intuition on how this could be extended to other robotics applications?
Yeah, so the centroidal model is simpler because it just has one single rigid body that we need to regularize. While in the Ford model, you also need to worry about, you don't want the joint velocity to be too large so that you get some jittery behavior, etc. So you need to regularize a lot of behaviors like joint jittering and also high full impact, etc. While in the centroidal model, you only need to worry about one single rigid body. That's why it's much simpler to design a reward function. And what's the second part of the question?
Oh, yeah, the second part was, what's your intuition on how this could be extended to other robotics applications? And my question is going to the side that, doesn't this replace reward engineering by some sort of state engineering?
Yeah, so here we basically borrow intuition from model-based control community so that because they find that this potato model can already can do a lot of agile locomotion on their quadrupedal robot, and we directly borrow that. But eventually it will be limiting because it's still based on human engineering kind of, and hopefully we can also learn a simplified model from data and then use those learn simplification to do reinforcement learning, and that can be extended to more applications like manipulation kind of thing. Yeah, but I'm not sure how we can do that yet.
Thank you. We have time for one or two more questions if there's any more.
Hi, I had a question for Kong Wei about the underwater drift cam robots. This is more about the robots themselves. I was wondering if you could explain, you showed some examples of those robots. I was wondering like how much time do they spend underwater doing their mission? And then how are they recovered at the end of the mission? Thank you.
So how much do they cover?
How long a time are they underwater?
Okay. So that robot is kind of so it's very passive horizontally, but it can only control its buoyancy. So it's move very slow in the ocean, and the time duration could be so there. Time duration could be very long because it's very energy efficiency. I mean, because the control principle for that robot, it does not cost much energy. So it could be months. Yeah.
So I think that just about wraps up our session. I want to thank the speakers again. This was amazing. Even what you called the boring parts, I think were really fun for us. So that was really fun. So I'm going to turn it back over to Michael, and he's going to let us know what we have to do.
Awesome. Thank you very much. Okay, we have lunch for you set up outside. An option, you have the ticket for that. You have a special cordoned off area with your vegetarian, vegan options available. Everybody else, there's kind of chicken fajitas here. Everybody's getting fajitas. It's chicken or veg, but I want to make sure that the people that signed up for the veg get the veg. So we're going to be checking for those tickets in the back. Enjoy. We resume here at 2 o'clock for the open problem session. engaged, and they can't hear anybody that doesn't talk through a mic. So,
all right,
take it away.
Yeah, well, hi everyone. So I'll fully admit this isn't really an open problem in the sense that I think we're going to come to a great solution right now, but I think it's a common annoyance at least. So let me describe it and see what people think and if they've encountered this kind of thing themselves. So basically in planning, right, you have a set of feasible solutions. These satisfy your hard constraints, complex set. And each solution can be evaluated with multiple objectives. Let's call them F1 through Fn. And in the talks this morning, we saw several different objectives already, right? Someone was talking about the probability of collision in the motion planning problem with uncertain obstacles. There's path length. I heard jerk mentioned. There are things about the bending energy or the curvature, or there's a whole set of different objective functions we could use. And generally you'd like to minimize them all. It's good to minimize them all, but they compete with one another. And so you have necessarily trade-offs. So what do you do? I'll give you a few ideas on what you do. I think the second one is the one that people most commonly use in this case. But the first one is maybe the theoretically potentially most appealing, which is you find the Pareto front, right? So that's the set of all the solutions that are not dominated by another solution. So just to be clear, so we know what we mean with dominated, it's that a solution S is dominated by another one, S bar, if that S bar has a lower objective value for all the objective functions, and there's at least one where it's strictly better, right? Otherwise, if they're just the same for all, then we don't say either dominates. That's hard to compute generally. And even if you did, you're not done, right? Now you have this complicated subset of the feasible solutions, and you still have to pick one from that subset, right? So it's not like the Pareto front's the holy grail in some sense. You still don't know the answer at the end. I think the most common option is linear scalarization, where we take a weighted sum of the objective functions. And the key drawback to this is, how do I choose the weights, right? Someone has to come up with the weights. And the other thing, and I'll only mention it briefly, is that it's not Pareto complete. That means you might find the minimizer for a particular set of W's, but there actually is another solution that dominates it. That's what not Pareto complete means. Okay, another option, which I think people do, myself included sometimes, is, okay, I've got too many objectives, let's put some in the constraints, right? Take some of the objectives and turn them into constraints of the form Fi of S is less than or equal to Bi. And I guess my question there is, have we really achieved anything? I still have to pick the right-hand side of the constraint. So I don't have a Wi, but now I have a Bi instead, right? And then there's alternate methods of scalarization, so that actually solve this Pareto complete idea instead. So instead you could solve minimize over all the solutions S the maximum of the weighted objectives. And this, again, you have this problem that how do I pick the weights? But now at least this is Pareto complete. If you find the optimizer for it, there's not going to be a dominating solution out there. So anyway, this is my long preamble to say, what do we do? How do you, and maybe just even, it would be interesting to hear from different people, how do you proceed in this conundrum, right? Of multiple objectives, and you need a way to deal with them. And just my last thoughts on things that make this hard or interesting is, generally these objectives have different scales, different units, and so they're not even comparable. How do you compare the probability of collision with the path length? 7 times the probability of collision plus path length, is that good? I don't know, right? Also, even if you knew, I care 2 times more about probability of collision than path length, does that mean I pick the one weight 2 times as large as the other? The translation isn't that clear. Is there really a single set of weights, or is it just specific to the particular task and context that we're kind of thinking about? And then also this idea of kind of prioritizing or nesting optimization. So I pick an outer objective, and then optimize that and then optimize the second one subject to a constraint that I found by optimizing the first and so on, you know, like something like this. So anyway, that's the end of my preamble. I'd be interested to hear people's thoughts on this. I see.
I'm going to do my best to get people in the order that I see their hands get raised.
Hi. I think this is a great problem. I don't have an answer to it. I just have an observation to make. This seems to be very similar to the alternative. If you decide what the weights are, then it looks very similar to the alternative direction method of multipliers, the ADMM, which has, you know, in the past decade, people have done a ton of research there. They have centralized solutions. They have decentralized solutions. There exist analytical gradients on how to kind of accelerate the convergence rate. This is exactly the form of distributed optimization. You don't necessarily have to say it in a distributed way, because even you have one agent, you can do something like divide and conquer to accelerate the convergence of your optimization. This is, you know, just one takeaway that the problem you describe, the problem formulation you describe, if you find those weights you said, then it's, you know, ADMM is the way to go. One very good way to go.
Yeah, interesting. Okay.
Over here, surprise. Nope.
Yeah. Oh, hi. Sorry,
comment.
I saw another mic.
One thing that I think may be interesting here is if you imagine, okay, the parameter space you're optimizing over, that is, what do I want to say? Nope, I messed it up. Consider the weight space, and then for certain collections of weights, they all lead to the same Pareto optimal, right? So there's an implied cell decomposition in the weight space, right? Which is an interesting kind of computational geometry problem, perhaps, in different sorts of contexts. And I don't know what it ends up looking like, but that's one possible thing that one could study if they haven't already. And then the next thing that might happen is, imagine you have a system where the priorities are a dynamical system. So the weights change over time as the system gets used. Some things might become more important, like the price of gasoline goes up. So now you want to optimize gasoline instead of how fast you can get somewhere and stuff like that. And then the size of those regions start to matter, right? Because maybe there's big regions of weights over which, you know, that's like a very stable, you can make like a dynamical system stability kind of analysis over weight space. Anyway, just some extra thoughts there.
No, it's a great, so what you say is actually, it's exactly right. So we've done a bit of work on identifying what we call equivalence regions, which is just the set of all weights that lead to the same optimal path, right? Or for which the optimal path is the same. And there are some nice properties, like that set's convex. Computing it, though, and the extent of it is not easy. I mean, Nils, who was a PhD student with me, is now a postdoc at Delft. He's been doing more work on that than, you know, is more of an expert on that than me, but that's definitely a great observation. And I don't know exactly how it helps you in solving this right now, you know? Like, yeah. No, but thanks. Yeah.
So one potential issue I just thought of is when a situation might be Pareto, let me see, part of the Pareto front and possibly found when you make the weighting, but still isn't good. And I was thinking the hypothetical, let's say you have there are two constraints and they compete, and you can make one of them good and the other one bad, one of them bad and the other one good, or you can get them both really mediocre. It's possible that if you weight them both the same, you will end up selecting the solution that is mediocre in both of them, even though really it's okay to have one of them be quote unquote bad, but having them both be really meh is actually a strong negative. How do you account, and I'm just thinking, how do you account for that kind of situation where weighting them, they might be equally important, but you still need at least one of them to actually be good. And so just going for a happy medium that ends up satisfying neither condition especially well might actually be a problem.
Yeah, and maybe for this, you need to explore a little bit the Pareto front, right? To get a little bit of an understanding of what are the trade-offs available, right? To even know like how low can I push this objective function? How low can I push this one, right? But it's exactly the trade-offs that you're trying to figure out, I think. Yeah.
So quick question. Have you, I mean, I'm not a sort of biology person or a human robotics person, but have you looked into sort of how sort of humans or some biological animals solve this kind of problem? You know, I'm sure, for instance, like a rat probably needs to find food, but also needs to know where it needs to go, right? They're coupled, but where does the importance lie? And have you looked into that?
Yeah, I have not personally looked into like biological inspiration for this at all, which is it's an interesting direction. I mean, one thing that we have looked at definitely is, you know, where these weights are the internal weights of a user, right? And so you're trying, they can't write them down on a piece of paper, but you're trying to understand or learn from them what they are. And so there you're kind of trying to query them potentially through solutions and asking them, which do you like better, right? So, but I don't want to talk, you guys talk. Oh, yeah.
Hi. So this is happens to be related to the last question, but I think like instead of saying maybe like the algorithm doesn't know how to choose which solution is the best, given that, you know, there are many solutions on the Pareto front, maybe is it like more reasonable to say that like we don't actually know what we want? Because I think if we know exactly like which one is more important, or like what constraint we should set on each objective function to achieve what we want, then maybe it's like a simpler problem. Yeah.
Maybe what you're kind of saying is like the question's not even that well posed or something. Like there is no single set of weights to use, or almost, right? Like you can't expect to find them. I'm not sure. Is sorry, Mike's gone. Yeah.
So I'm not suggesting any solution over here, but I have a question. Like, suppose, like in the presentation today, Dr. Rush, he's proposed one of his algorithm, like graphs of convex sets, and then in one of your work, there was one of your students is trying to find the regret bound. So suppose if we combine some best methods like with different objectives together, I just want to know like combining these best methods will give us a best solution, because robotics is expanded in different fields and we are trying to make robots intelligent and much more safer for humans. So this is one of my like the thought process, or like how it will be. Have you ever given a thought on this, or how do you think it can, I mean, will it work?
I'll also admit I'm not an expert on how to solve this. I don't. It was just I was approached on presenting an open problem. I thought this might be fun to talk about, and I don't really know. I guess what you're talking about seems more like a solution method to me, in that like if I had a good solver for, or a method to solve with objective A and a method to solve with objective B, then potentially it could allow me to better solve a combined objective. You may be right, but you're also right. Like I think Russ in your talk, right? It was like on slide 32 or something. At some point, you presented an objective, right? And it had 3 terms in it. It was something plus A times one term plus B times another term. And I guess I mean myself included, you just say, oh, let's leave it up to the user, right? They'll pick A and B, and they can pick it how they like, right? But how do they know how to pick it either, right? It's in the end, I guess it's just an iterative process. You pick a value, you see what you get, you see if you like it. If you don't, you try and tweak them a little bit. It's sort of like maybe can almost look at methods people use to tune PID controllers or something, right? Like where you have 3 parameters and experts know how to do it. You turn down the integral gain until you see something on, I don't know, there are crazy rules for it. Anyway, sorry.
Yeah, so I guess this also kind of follows in similar thread to what other questions have already posed, but I'm just kind of wondering maybe what other people would think, like the nested optimization approach here is kind of fundamentally different from like the linear scalarization. And I'm just kind of like wondering if there's any consensus on whether linear scalarization is ever just not sufficient as an approach fundamentally. Like for example, you know, maybe going back to the question on how biological systems would approach this problem, like if you tried to do IRL with a linear scalarization, would you ever just not be able to find a set of weights that match what you see a biological system would choose? Or
yeah,
like,
that's a
do we
great
ever,
question.
Like, strictly need something more like nested optimization?
Yeah, I mean, I don't actually know. I mean, I'm saying this over and over again. I don't really know the answer to that, but I think that's an excellent question, right? It's like, what are some good examples where linear scalarization is kind of not enough? Maybe Dorsa knows more. I don't know. Maybe not. Just we use this model like a weighted sum of features a lot, right? And it's convenient, it's clean, right? And then.
For specific context, like if you find that your can't fit weights to a certain setting, does that just mean your features are wrong, or like is there something more like it goes beyond how you set up the problem?
Yeah. I mean, I guess in theory, when you have these multiple objectives, your Pareto front can be non-convex, right? And then at those non-convexities, the linear scalarization can't capture those solutions. And so if the true solution you're looking for is in that portion of the Pareto front, you can't capture it with any set of weights. That's my understanding. But I don't know how often that occurs, right? That like, or a good example where that's a true limitation.
Okay, so this open problem, we have time for 3 more questions. There's 2 mics already out in the audience, and we have an online question. So I'm going to ask the online question, and then we'll do the 2 mics that are still out there, and that will conclude our first open problem. It's been a great kind of discussion so far. So the person online, who is it online? Dale McConaughey. Apologies for mispronouncing name possibly. So, kind of a point of suggestion or adding more to the conversation. It's possible that, you know, it may only be necessary to satisfy some subset of the constraints. You need certain things to happen, but maybe you can trade meeting one constraint for meeting some completely different constraint.
Say that last part. I just missed the.
You can like you need at least some higher level logic. Sorry. There could be an alternative problem formulation where the higher level logic of the problem dictates that you must meet either one constraint or some other constraint, or potentially a generalization of that where you have to meet a certain number of different constraints subject to some higher logical process.
Yeah, that's interesting. Yeah, I'm not sure. I see what you're saying. Maybe like you instead you pose them as some number of constraints, and you say I need to satisfy at least k of them, or something like that, right? I don't know if that helps or just made our lives even harder. You know, but it's an interesting idea. Yeah.
Just put them into objective. Just then you satisfy as many as you can.
Right.
Okay, where are my mics in the audience? Who has a mic currently? Kostas.
I suppose in the domain you're working on, aren't people trying nonlinear ways of combining features? You know, try to learn a network over some features, and why a linear combination of weights?
Honestly, yeah. I think I was wondering if when someone was going to say that. I think that's right. You know, there's no need to do any of the things I listed. I think this is the one that if I just think of papers I read or review or that's the one I see most frequently, right? But I guess the idea maybe in this is that the individual functions are a little bit simpler in some sense, right? Like they might be path length or something that's convex. And then if instead you try to combine them into this massive nonlinear function, you haven't made things any easier. But I don't know if that's right or not. For sure, I think that's right. Yeah, there's not always going to be. I don't think my internal representation of how I evaluate food is like a weighted sum. Maybe it is. I don't really know.
Okay, time for one quick last question, and next question usher, please start getting set up.
Yes. So it's just a thought or an observation. I think that we're experiencing a challenge here because maybe the tool that we're trying to use doesn't fit the problem. So we're trying to use optimization to determine preference between when the units are different, right? So maybe just optimization is not the right tool for that. And I've just been like thinking not too much about it, but maybe instead of optimization, we should go for something like satisficing. Because you mentioned, for example, an experiment with humans that you present them a solution, you ask them, is it good for you? This is more of a satisficing question. Does it feel good for you? Does it satisfy what the objective that you want to pursue? And I think that intuitively, this would be a more suitable to this problem that we're trying to solve. It's just a thought.
Yeah. No, thank you. Yeah. Well, thank you, everyone. Appreciate it.
Thanks, everybody.
Thank you.
Thank you. Okay, our next question poser for the open problem section is Elon Ramon. And we're going to follow basically the same format, except for he is going to use the board, I think, or maybe just not the board at all.
Just put it in my pocket. Thank you. So I was told we have 20 minutes, so I just set my timer.
Do you need the board?
I'll use pens, board, and the big apology. I prepared my open problem this morning. Assuming that our organizer will say, oh, it's too late. They say you're in. So it has to do with a completely different viewpoint, robot inverse kinematics. Are you all familiar with the inverse kinematics problem in teaching robotics courses? So the robot gripper has a fixed position and orientation, and you have to solve for all the joint values that realize this position and orientation of the gripper. So we are working with the problem of inverse kinematics of only 5 end conditions: position of the gripper, 3 degrees of freedom, X, Y, Z, and 3 orientation parameters. 2 orientation parameters. So our inverse kinematics problem, we have only 5 conditions. Okay? So inverse kinematics. Three positions, 2 orientations, practical examples. Excuse for my terrible spidery writing. Grasping objects which have a circular symmetry, like water bottles. So we don't care about the orientation of the gripper, about the axial symmetry. We just want to have 2 degrees of freedom of orientation and 3 positions. So in the kinematics, we have 5 end conditions. Therefore, our understanding, we need a robot with 5 degrees of freedom to solve the problem. We don't need 6 degrees of freedom robot. So our robot arm let's say like 5R, just as an example, doesn't have to be any 5 joints. So in that case, the number of inverse kinematic solutions is discrete. Question number 1, it's a series of questions. We are looking for research partners. Parentheses, we're working on it for already 2 years, stuck on it. We need somebody to get us out of the local minimum. Question number 1, what is the number of inverse kinematic solution for this problem? It is known that for 6R robot, complete position and orientation, there are at most 16 solutions. So let me repeat it. We have 6R robot. I specify 6 end conditions. The well-known result is that it is a tight lower bound. There are 6 examples in which the number of solutions to the inverse kinematics is 16. What's the bound on the 5R robot? What's the number of solutions, lower bound? So question number 1, number of solutions. Question number 2, this is how we are going to plan to attack this problem in general. We think about the workspace of a 2 revolute joint robot. Did you ever realize it's a torus? Let me show you what I mean by that. Sorry. Okay, so I don't want it to break. I'm in teaching mechanical engineering. I better strengthen some stuff here. So the idea is, look, the workspace is generated by 2 circles. I have now a gripper which sits maybe right here. But there's no joint here. So when I rotate the joint theta 2, I get a circle. Okay, this is part of the workspace of the robot. Now I take this circle and rotate it about theta 1. I get a torus. It's called the general torus. Let me take the circle and rotate it about the z-axis. So you get something which is roughly, something like this. And that's the workspace. Okay? I'm saying an important sentence. If the 2 axes are orthogonal, mutually orthogonal, it's called the right torus. But in general, and for robot arms, this is not a right torus, but just a general torus, 2 generating circles. So I'm arriving to the main question. If we have 2 such robot arms, each one is only 2 joints, RR robot looking at another RR robot, and they just want to handshake the grippers. We want the center of the grippers to reach a common point. Geometrically, the problem is take 2 tori in space, intersect them. We have an assumption, we are not able to prove it. The number of intersection curves of 2 tori is at most 4. Okay, and this is my big question. How do I erase this stuff here except with my hand? Is any? Oh, thank you very much. Question 2. Any other pen? Here it is. Question number 2. That's the central question. T2 cross T2 at 4 cross. Yeah, I can give you some ammunition. If you look at the top view of a torus, okay, top view, the number of intersection points of an ellipse with a torus, if I understand it correctly, I just did it like 2 minutes ago, it seems to be 8 points. I think I'm correct. Steve, you watch my back. 1, 2, 3, 4. 1, 2, 3, 4. 8 points. Okay? So we were able to prove the following fact. If you take a toes, a two-dimensional toes, a general toes or right toes, intersect it with a circle, not an ellipse, 4 points. Okay, so we proved it algebraically. So if you take a toes, intersect it with a circle, try me, maybe here. It's a circle, it's not an ellipse. 1, 2, 3, 4. So we can share with you the algebraic proof that the intersection of a circle with the toes at most 4 points. The question is, how can we show using any approach algebraic? Look, hand waving, we're almost sure the assumption is correct, at most 4 curves. We want a proof, algebraic proof, why it is at most 4 curves. We're working on it for 2 years, stuck. Let me show you, it's really interesting to know it was solved for the right toes problem by a Korean PhD student. He did the following amazing thing. He said, if the toes is a right toes, remember the 2 axes are orthogonal, the right toes can be generated by rotating a sphere about a circle. So the sphere is like the inner sphere, you rotate it, you generate the toes. So he said, let me build the configuration space of one of the 2 right tori by shrinking this sphere to the point and expanding it. So remember, the sphere like now has to touch the toes. So the configuration space, I can shrink the sphere to a point. And I'm getting a little lost here because I'm supposed to get 2 tori as a result. One is outward. The inner one, I lost it, but they're supposed to be the boundaries of the configuration space obstacle. So I converted it like to a motion planning problem with configuration spaces. So one of the tori was shrunk to a circle. It's a generating sphere. He pressed it into a point and somehow generated like an outer toes and an inner toes, which I'm missing the inner toes. And then because it was shrunk to a circle, the other toes we didn't touch. It reduces to the problem of intersecting a circle with the toes, and he has like an inner toes. Again, I lost the inner toes where it is. Outer toes get at most 8 points. You can pair them and get 4 curves. So let me just repeat the question. Not right tori. For right tori, we know a general toes that I just plotted cannot be generated by rotating a sphere inside. There's no way. The cross-section is really thick. And let me just finish this open problem by saying where we are heading with it, why we are interested in this problem, because we said we are going to solve the inverse kinematics problem by actually allowing breaking our 5 degrees of freedom chain into 2 robots. So we have like 5R. So we take R, 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 R. So this one, let me just put it like this. It is based to the ground. This is where I have my gripper sitting right here. So our approach is we cancel out the middle joint. We have an RR chain based to the ground. We have an R, so this is like an RR chain to the desired position in 2 degrees of freedom for orientation. Okay, so now what is happening, we are going to replace this joint by a spherical joint. Do you know what is a spherical joint? It has 3 degrees of freedom. There are some mechanical engineers here, 3 degrees of freedom. So total number of degrees of freedom is 1 plus 1 plus 3 plus 1 plus 1 equal 7. By fixing the gripper, we actually locked all 6 degrees of freedom. So I remove 6, I get 1. So the closed chain, RRS, RR, is a 1 degree of freedom chain. Now, if we break the spherical joint, here's what we have. We have two RR robots. Each one has a tori workspace. All the points where the center of the spherical joint can match are exactly the intersection curves of the two tori. So in theory of mechanisms, people are asking, give me a closed chain of 1 degree of freedom in 3D. What are the number of assembly modes? This is how they call it. Then it's an open problem. Does a closed chain with 1 degree of freedom, there are whole papers with catalogs, all 1 degree of freedom closed chain in 3D. But nobody knows whether, and the assumption is they have at most 4 assembly modes. So it has 1 degree of freedom, so it can live along 4 curves in space, this closed chain. Once we solve this problem, here's our trick. If we know that this chain is 4 curves, in order to solve the inverse kinematics problem, it reduces to solving the inverse kinematics problem on those 4 curves. On a curve, you can do a optimization like gradient descent, checking all the local minimum. You can define a cost function. When the cost function is 0, you get exact matching of the original 5R chain. So let me just go back down to the ground level. So there's all this machinery hiding inside. 2 tori, not right tori, 2 tori, help us prove that they intersect at most at 4 curves. Or save us our precious time, give us counterexample. There are more than 4 intersection curves. Please.
Okay, excellent. I think that we have time for about three comments and questions here. This is a very interesting topological question and well within the meat of the WAFR.
Hopefully. Can you put off, Tobias, take off the mask for a second?
No, just to understand the problem formulation, if you intersect the torus with itself, you get infinitely many curves, right?
Oh, you have two different tori.
Assumed to be different. What are the other assumptions? Same size and.
So you have 2 different robot arms. Each one is 2 degrees of freedom.
Mm-hmm.
And the workspace of each robot arm, if you look at the center of the gripper, is a 2-dimensional torus. It's a surface.
Okay. And they have the same sizes?
No, they're completely general. No, they have different sizes and different
center
angle between the joint axes.
Okay.
So there are 2 general tori. Forget about the robots. Just give us the intersection of the 2 tori. At most 4 curves.
Okay, thank you. I would need to think about it. But just to
and no
take out the trivial solution.
Not just the efficient algorithm to compute it. Bounds, hard bounds.
Okay, thank you.
Okay, we're gonna ask 2 more questions.
So for your first question on computing the number of solutions in the inverse kinematics problem, don't you just need to compute the mixed volume of the system of equations that you have?
Compute what? I missed
the mixed volume of the Newton polytope of the variety that you've described.
So maybe you can explain it. I know there are algebraic techniques to solve the inverse kinematics problem with 6R robot. I think it's an eigenvalue problem.
So
it's like 16 by 16 matrix. But you're telling me that what the bound on the 6R robot implies also the bound on our problem?
So you have an inverse kinematics problem.
Yeah, the usual one, the classical one.
Just a classical inverse kinematics problem, and which you can rewrite as a system of polynomial equations, right?
Yes, correct.
And then you want to count the number of solutions to the system of polynomial equations?
Yes, but now I have only 5 degrees of freedom and only 5 conditions.
But it's still you want to count either the dimension of this solution space or the number of solutions.
Yes, and
so
do you have any insight? You think
there's like a classical problem in algebraic geometry where you either want to compute the dimension of the variety or you want to compute the mixed volume of the system of equations of the Newton polytope.
So you're saying, because I never studied these tools, so you have a method to actually compute at least a lower bound, or we need a lower bound on the number of solutions. So you think this is the right way to get it?
Yes.
Perfect. So can we chat a little? Thank you very much.
Yes, I think this is good. Do we have one more question? Anybody? Okay, so
Thank you.
Well, my quick question then is there any kind of relationships here between parallel robotics that we could leverage? Because forward kinematics versus inverse kinematics, kind of one way is difficult, the other way is easy, but that changes if you're doing kind of parallel robotics versus a normal actuator. So when you link up, it seems that possibly you get into the world of parallel robotics where there's this switch in what becomes easy and what becomes hard. But I don't know enough about that subdomain to give you any helpful information, probably.
So parallel robotic, anybody knows there were like tools developed for the number of solution curves in part? There are.
A little bit, but for example, for a Stewart platform or something like that, the inverse kinematics and the forward kinematics, kind of which one's easy, which one's hard, are opposite of what we normally kind of experience in like a forward manipulator.
Sure, we didn't look at it. And also I know that it switches difficulty. So I'm not sure this will help here. Look, the problem is really simple. Take two toroids, intersect them, show us at most 4 curves. It really boils down to that.
Okay.
Thank you very much.
Excellent, very good. Steve Laval, come down and get set up. And as you're coming down, I will remind everybody that there have been wafers in the past where a problem that has been posed at the open problem session has been solved over the next year or so and then submitted to the next wafer that happens 2 years later. And those are papers that we very much like to see.
Now? Okay. Great. Okay, so somehow I got tricked into doing this, so hopefully it'll be entertaining enough. Try to fit it on the board here. All right. I'll start off with a small joke. So ask a control theorist to come up with a simple polygon. And they go like this, more or less without curves. And then you ask a computational geometer to come up with a simple polygon. They go like this. There's no insult to control theorists. It's just in fact, I'm making more fun of the computational geometers. So suppose you have a simple polygon. That's the beginning of my talk anyway. And the title of this sort of open problem or sort of challenge, I'll call it the Van der Korpet bounce. There's no colors here, right? This is going to be a black and white old style talk. So, okay, fine. So at some point over a decade ago, I got kind of tired of avoiding obstacles. And I thought, what happens if you just hit them and then look at trajectories that just kind of bounce off of them? Or if you have a robot, maybe it comes up really close and almost bounces and hits and then just turns and goes away. So so you can start thinking about what would really long trajectories look like that just kind of keep hitting off the walls. And there's some angle at which they bounce and they go running around doing stuff like this. And it's kind of hard to draw it without different colors, but it goes on for a really, really long time. And a lot of this was when we were looking at these problems, we were studying ergodicity and billiards, and my former student, Leonardo Bobadilla, did a lot of these things. But a couple of things that are known here, or a couple of different strategies for bouncing. One possibility is, I'm really gonna run out of space. How far down can you see here? Maybe I can, okay, let's see. A little bit here, okay. All right, let's see. So, so one possibility is just a random bounce. So if I have a little goal region here, let's say, it's non-zero measure goal region, if I just do this random bounce, every time I come up to a boundary, I go in some random direction. Oh, the gift of color, thank you so much. I want to personally thank you after the talk, so that's, well, too late for that one. Oh, that just erases it. Okay, well, anyways, I won't go back into that. So, oh, the goal can be green at least now. That'll be nice. Wonderful. So I think we're going to hit that with probability 1, right? If every time we come up to a boundary, pick a direction at random, uniform random, 0 to 2 pi, and then go, And I think we'll all believe that if this is a goal of non-zero measure, we'll hit it, right? With probability 1. Everybody believe that? I'm just going to state that. Somebody must have proved that somewhere. It's not too surprising. I think it's a little bit weirder is if I do a billiard bounce. I live in Finland, so I'll call it the hockey bounce. You have a hockey puck and you hit it really hard, and this is on ice, and you just let it go pink, 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 pink. So the angle of incidence is equal to the angle of reflection, right? Somewhere in some physics books, they have those things. So you know, it's just a perfect like mirror-like bounce, right? If you do that, what happens for sort of, let's say, arbitrary simple polygons? Well, in 1986, it was shown by Kerkhoff, Moser, and Smiley that for almost all simple polygons and almost all initial configurations, the trajectory that you get is ergodic, right? Which means ergodic with respect to the boundary here and all possible orientations. So that's S1 cross S1? I don't know. Anyway, it's with respect to that boundary. So no, it's S1 cross R, I guess, because there's only so many directions here. Anyway, it's ergodic with respect to that. So that's really interesting. That means every open set on the boundary is going to be touched. So that means it's called topological transitivity in some of the billiards dynamical systems literature. Well, incidentally, mathematicians have studied these a lot. They're called mathematical billiards or dynamical billiards. It goes back to well, it goes back a long way. Maybe you can start to even work in Poincaré and Birkhoff in the 1930s and such. But then I think a lot of it comes out of Russian mathematics. So the students of Kolmogorov study this a lot. Sinai, who's still alive, I believe, and Sinai's student Bunimovich, who I think is still at Georgia Tech, if I'm not mistaken. But anyway, they used to use these problems to like torture students of Hamiltonian systems because it's like a special case of a Hamiltonian system, but it's kind of weird. It's volume preserving flow. But anyways, there's a whole literature to these kind of things. But it's quite interesting. It surprises me quite a bit that just doing the same kind of bounce rule lead to trajectories that get pretty good coverage. So now imagine I could make a planning algorithm that just works by bouncing like that, and it seems to work pretty well. And maybe when you're done, you have a trajectory that's too long, so you apply your favorite optimizer and just shorten it, right? Is that a good algorithm? Or maybe your learning algorithm is stuck or your optimization method is stuck. Where you normally do random walks, you might want to do something like this, just go bouncing around. We can make higher dimensional versions. That's sort of fun. It doesn't quite get to my question yet, but I just want to say that, again, for almost all simple polygons and almost all initial conditions, the resulting trajectory is ergodic. I'm not saying what that is exactly, but I'll just say it's very strongly, uniformly visiting everywhere. The frequency of visits to a place along the boundary will be proportional to its measure only. That doesn't matter where it's at. So that's really quite strong and powerful. It's not necessarily a probabilistic statement. It's just something that happens with frequencies and such. Oh, and by the way, the almost is in the sense of it's except on a meager set. So it's not on a set of measure 0. That's another problem. So it's another, I don't know if you know about meager set theory, but it's some other weird thing. Look up fat Cantor sets if you want to have fun with in meager sets, but I don't want to go down that path, but it's a little bit of weirdness here. So it's not just except on a set of measure 0. That's like easy almost. It's a more complicated almost. So that's fine. So now it's getting into my sort of questions that I have. I started wondering, okay, this is kind of a simple fixed bounce law. The random one seems to have nice properties, but I wonder if I can do better by replacing this randomness with deterministic sequences, which I've wondered about for a long time in motion planning. And I got really excited about Van de Corput sequences at some point and generalizations of that. Let me go to board number 2. All right, it worked. Hopefully this surface is writable. So if we go to the old, let's say, Van de Corput sequence, so maybe we have the interval 0, 1 here. And how do we sample Van de Corput style? We pick 0 and then maybe 1/2 and then maybe 1/4 and then 3/4. And let's see if I can get it right. Then I think it goes, the 8ths start coming. I think it's this one and then jump over here and then this one and then go over here. I don't know if you remember seeing these things, but you can just count in binary decimal and then reverse the significance of the bits. And then you'll go jumping around all the time. So rather than just flowing across gradually, you keep jumping back and forth from half to half or in higher dimensions, quadrant to quadrant and so forth. Now imagine doing a topological identification and just let's just say that this point here is the same as this point here. So now I'm doing Van de Corput on a circle, it feels better on there somehow because this kind of stuff wasn't getting much love on this side anyway. So now you can do Van de Corput sampling on a circle. And now I can start wondering about doing Van de Corput bounces. Every time I come to a wall, I maybe just pick the next point in the Van de Corput sequence and I make some dense sequence of bounces now. And I want to ask, what does that give me? Does it help with anything? Does it make it worse? It probably doesn't make it worse, but I should be able to get some nice deterministic guarantees. Can I do better than accept meager sets, in terms of being able to sort of conquer all polygons? And maybe life gets better in the sense of more efficient exploration. I'm not really sure what happens. There's also different ways to define it. So one way to do it, I'll kind of make the polygon look like a circle here. And let's say this is 0 point. I don't feel like multiplying by 2 pi or something. So I'll just say 0, 1/4, 1/2, 3/4. They're really tiny. I forget how tiny this board is. 1/4. So maybe a kind of Van de Corput bounce, at least on a circle, looks something like this, where I just go. I just have to do the same kind of pattern here. So maybe I start off here and I go over here, and then I guess I go to 1/4 and then 3/4, and then where did I go? 1/8 maybe, and then over to here. That doesn't look too good. I don't know what's going on. Maybe it goes over here, and then here. Anyway, it does some kind of dance around like that. That'd be a kind of Van de Corput bounce on a circle. But in other ways to look at it, I may call that like circle-based coordinates, perhaps, in doing some kind of Van de Corput thing. But another way to look at it, another alternative definition trying to make something like this, I look at the angle that you're coming in here, and then, actually, maybe I'm going to ignore the angle that I'm coming in, and I just think about, with respect to this surface you're bouncing off of, I want to pick an angle here, theta, and I'll just pick that from the Van de Corput sequence, scaled by pi or something like that. So what does that do? I don't know. Go simulate it. I'm not sure what'll happen. It's not that hard to write a little Python code before the reception tonight and show me what happens. It's not that hard, I think. So go through the sequence and see what happens. Another way to do it, this one I would call like a local frame version of it, because it's based on exactly what happens at each one of these points. I guess I could make another kind of global frame version where, each time I'm bouncing, the angle's not with respect to the surface, but with respect to a global coordinate frame. And then, whatever the theta might be after the bounce. Oops, I guess I was drawing it this way, kind of. Whatever that theta might be, it's always in a fixed global frame. So you could have global or like inertial frame kind of Van de Corput sequence bounce, or you could have a local frame based one. And quite generally, there's a whole family of things one can study. You can look at the angle you're coming in. Let's say it's alpha. There's the angle of the surface, call that beta. And then there's the angle that you decided to go out, theta. So somehow you have some function. You'll say theta equals some function of alpha and beta. And I'll put little eyes on here because I'll say that you can kind of let the function vary as it goes along the sequence. And so there's all kinds of things one can do here. And it's intriguing because the random one seems to have good properties, but then randomness doesn't always have great properties, especially if you want deterministic guarantees. The billiard one does amazingly well, but I wonder if we can do better by doing some kind of sequences here. In fact, maybe there's only 2 different kinds of bounce rules that you switch between back and forth forever. It won't be as fancy as or complicated as the Van de Corput sequence, but maybe that will be quite efficient somehow. So there's theorems one can prove. There's at least some insights you might gain from just doing basic simulations. Draw your favorite polygons and give it a try and try some different bouncing rules. Of course, there could be higher dimensional versions of this. And again, maybe you're trying to unstick optimizers. Maybe you just want to do coverage planning. Maybe you want to just reach the goal. A number of different things you could try, but that's kind of the general direction. Maybe there's a family of open questions and here are a lot of things one can answer, but it just kind of bugged me that there's this kind of missing piece here where I think determinism is useful. These dense sequences could be quite useful, but I can't quite, and yet a fixed bouncing law, it's not fixed angle exactly, the billiard one, but it's a kind of fixed law is doing something wonderful almost always except on a meager set in polygon space and initial condition space.
Okay, thanks. Another great open problem for the session. Please raise your hand if you have feedback, and I will run around with the mics, and other people will also run around with the mics.
maybe I'll just keep rotating it. You can like see because people have different viewpoints here. I don't know. You can see
So I was just wondering, could you explain the significance of the polygon being simple?
Oh, thank you. Okay, it's so weird.
Because what difference does it make if the polygon? Suppose I'm like, what about a non-simple polygon? I'm going to stick another polygon inside your polygon as an obstacle. Like, what changes about the problem?
Yeah.
Why?
It might not matter so
Okay.
much. So yeah, I guess I just started with that by default. I can't say. In fact, now I'm tempted to go back to that paper from 1986 and see whether or not it allowed holes. I think the computational geometers have scared me enough to always start with simple polygons and work my way up. So, but
okay, I see. Fair enough.
I don't think in this case it's going to cause trouble, but you know, who knows.
Okay, thanks.
Right. Here.
Yep.
That's very interesting. We had this discussion with Michael. We were trying to address the same problem, kind of the same problem. So we were like between random sampling and van der Corport sampling, which is deterministic. And it turns out that it's not black and white. There's gray there. There are medium solutions. So what we ended up doing is we use the Latin hypercube sampling, which comes from the design engineering research area. So what they do there is that imagine that you have that the number of bounces, then you split your random 1D sequence to 5 bounces, and then you go to each segment and you randomly sample. Mm-hmm. In that way, you guarantee you have some assurance of 1D uniformity, and you also have not underrepresented area, because with random sampling, you have to have a lot of samples to ensure that you cover the whole space and you bounce at a certain direction every time, right? While with Latin hypercube sampling, you can use this property, and then you can say that you have this 1D uniformity without underrepresented areas. So this is something you may want to look at, and it also works with conditional Latin hypercube sampling, meaning you don't have to define at the beginning how many bounds you want. You may have 5 bounds and then build a new design, a new Latin hypercube sample, given the previous Latin hypercube design you had.
Okay, yeah, thank you. That's interesting. I didn't know about that. But also, when you were talking, it reminded me of, I've seen this kind of hybridization showing up in the quasi-Monte Carlo literature, where they'll do randomized quasi-random methods, which looks kind of like as if they cancel out, but they kind of don't. And there's like for example, I might want to generate a deterministic sequence on SO3, but I want to first generate a random element of SO3 to multiply in front of it. So that I could win at game theory and other things like adversaries and things like that, and make it more robust, but then still have the deterministic guarantees. And it sounds like you can get sort of the best of both, like that.
And the idea is that in higher dimensions, if you don't have one dimension to pick, but you have higher dimensions, this Latin hypercube sample works really.
Okay, Latin hypercube.
Latin hypercube sampling or design.
Yeah, thanks. Yeah.
Okay, so we have time for 2 more questions. We'll go with Stephen and then with Noah.
This might be, oh, never mind, it's working, sorry. Maybe I'm ruining your problem, or making it not as interesting, but I was just thinking like of if you thought of when the robot moved or it covered a swath, right? And then your only control is that you can decide like what angle you want to depart the wall.
Yep.
And then you could also just like ask the question, like, what's the minimum number of wall bounces to cover the whole region?
Yeah, that's interesting. That's reminding me of K order visibility problems and things too. I guess so there's like halls of mirrors and things like that, which are part of some of the related. If you go to computational geometry, then billiards, the closest thing to billiards is like Boris Aronov at somewhere in New York. Did a number of works on these kind of things. But you're adding thickness, so I'm not sure what happens there.
Yeah.
It probably gets really hard fast, I think.
Yeah, yeah.
Um,
We've worked in some coverage problems, so that's why
okay.
my mind went there. But anyway, it's just a
Yeah.
thought.
No. Interesting. Yeah.
Okay, last question.
So
Yeah, we started with these kind of things because we were fascinated by Roombas. Back in the days when they were a little bit dumber and mostly kind of zigzagged around, but they followed dirt piles very cleverly, and like wall following became dirt following, and it modified it into being no dirt, and it was really nice. But that's kind of how we started to look at these very simple bouncing strategies. And then I had some great Russian math friends who showed me these billiard problems and stuff too.
So the one that I was thinking is the van der Korput sequence is obviously only going to be defined on rational numbers, or rather it will only ever reach a rational number because it'll be 1/2, 1/4, not in this order, but 1/8.
Yeah, a very special subset of them.
And,
Yeah,
and
dense.
so,
Yeah.
of course, it is dense insofar as for any particular number you are interested in, especially a particular real number, you can get arbitrarily close to it, but you're still ultimately relative to random sampling, which will get you any angle from 0 to 2 pi, you are restricted to an infinite, but also infinitely smaller subset of those angles. Is that going to impact the potential results in a meaningful way?
Yeah, I don't think so. I think the main property you want is denseness of the sequence, and in any sampling scheme you do, you can either run it for a finite number of iterations, or you can run it for an infinite number of iterations, which is still discrete. And so you're always going to have a discrete set of points. So whether or not they're rational or irrational, or we multiply them all by pi or do some other kind of things, you're still stuck with it. So the point is that it's a sequence, which means discrete. Could be infinite if we talk about the limiting properties, and then it in fact needs to be dense, which means no open set left behind. Which is left untouched, which for these kind of problems, people, again, if you want to look at the literature, you can look for the word topologically transitive, which is a weaker condition than ergodicity. There's some stronger conditions of ergodicity too, but anyway, like mixing and other things. But I think this topological transitivity is all at least what I'm interested in here. So I don't think that particular technicality matters much from what I've seen.
Okay, that concludes our open problem session. Let's give Steve and all of the speakers another hand. We have our afternoon snack coffee break out in the same area where we've been having all of our food. The next session will start back here in 25 minutes at 3:30.
I apologize. I think the weirdos are the Are we trying to do the Arabic What?
It can be on. Yeah, it's already on. You can put it anyway. Okay.
All right. Very good. We have working mics. Do you mind if I for it for a moment?
Yeah, you're good to go.
All right, we're going to get started. Hello and welcome everyone to session 3. All right, take a moment to settle in. My name is Jaime Fernandez-Isaac, and I am an assistant professor in the Electrical and Computer Engineering Department at Princeton University. And I will be chairing this session. And as the co-chair, as a respondent co-chair, we're lucky to have Christoforos Mavrogiannis, who is a postdoc at the University of Washington. And I believe he'll be starting as an assistant professor in the new robotics department at U Michigan. So it's great to have you here. And yeah, we're going to have 3 talks in the session as we have in the previous ones. And it's the same drill as before. The talks will be 14 minutes. I'll do my best to keep the speakers honest. Then we'll have a quick minute for transitions. And then at the very end, we'll have the last 15 minutes of the hour for a Q&A. All right, so great. Without any further ado, I'll pass it on to the 2 speakers who I believe we have for the first paper, Hai Nguyen and Zihan Yang. Whenever you guys are ready.
Hi everyone. So today we are very glad to introduce our paper titled Hierarchical Reinforcement Learning under Mixed Observability. This is joint work between researchers from Northeastern University, Gallatin College, and the National University of Singapore. So our work is motivated by one observation, is that there exists some particular problem with partial observability. And solving this problem is equally sequentially solving goal-based subproblems with full observability. And we only have to deal with partial observability when selecting goals. So in the slide, there is a simple example. So in this domain, the agent, which is a mobile robot, and it has to reach to the unknown destination C. And because the agent doesn't know the location of C, so the problem is partially observable. And we assume that in this problem, the agent can localize fairly well in the 2D space. And in order to help the agent, there will be an important hint about the coordinate of C when the agent navigates to B. So in this problem, if we assume that we have some navigation policy, which I call go to G here, where G is some 2D coordinate, then we can just solving this domain by feeding the goals sequentially for the navigation policy to execute. So for instance, we can feed it to A and the agent goes there and it doesn't see anything. Then we feed it to B, then it goes there and it sees the hint when and the agent now can go to C. So because we assume that the agent can localize fairly well in the 2D space, so learning the go to Z navigation policy is actually solving a problem with full observability. And compute goals, we need memories here because we don't want the agent to kind of revisit a location that has been explored in the past, or we want to memorize the hints when the agent reaches B. So the way that we're solving this domain is actually similar to how humans perform some manipulation tasks, where the brain is the only component with memory, and it's gonna compute the design process for our legs and hands in order to achieve some design process. And the limbs do not have any kind of memory at all. So we use
a framework called motion-based mixed observability MDP or MOMDP to kind of describe those particular problems. So in this framework, a state, we have two components, X and Y, and X is fully observable, while Y is partially observable. Because X is fully observable, so it's also a component of the observation where we have X and Z. Z is another component of the observation. And we put three assumptions here for a MOMDP. And the most important one is the first one. It essentially says that the dynamics of the environment will be factorizable. And the first component of the first factors will actually be the dynamics of a fully observable underneath. And the other two assumptions essentially it say that the observation and the root function only depend on the next state. So going back to the earlier example, in this example, we can see that the fully observable component, that is the 2D cell position. And the other component of the observation is Z, and in this domain, that is the hint, which is only visible at B. And the component that is partially observable, that is the coordinate of the destination, which is unknown. And that one is a MOMDP by definition. But if we make the 2D cell position become partially observable, then that is not a MOMDP, because you can imagine that if we give the desired 2D position to the navigation policy, then the agent, there's no way that we can tell that the agent has reached that position or not, because the cell position is partially observable. And the assumption that the 2D cell position, at least at some point, going to become fully observable, actually a realistic one, because if otherwise, then the problem will be too difficult. So we introduced in this paper a method to solve MOMDP efficiently, which we call HILMO. And HILMO essentially, it is a agent with two levels. So the top level policies is a memory-based policy, and it takes in a high-level observation outputted from a summarizers, and then output a goal for the bottom level policy to achieve within K times step. And when the bottom level policies is trying to achieve the goal, the top level policy will stop acting. It will just rest until the next time step. And to create the high level observation, we investigated three ways in this paper. From the K observation emitted when the bottom level policy is acting, we can concatenating every observation here, to get a high level observation. Or we can just take the final observation in the sequence to create the high level observation, or we can put a recurrent layer, to summarize those observations into some fixed length vector. And between the top level policies, it is worth mentioning about non-stationarity in hierarchical learning. The problems arise when we try to learn policies when we try to learn two policies in parallel. So the problem arises because the same state action at the top level actually can lead to different outcomes, because the bottom level policy is changing. It can be exploring, or it is not converged yet. So the same state action can lead to different outcomes, and it kind of create applying the Bellman equation become non-stationary. And to kind of address this issue in our work, we use existing technique called high action transition. In this technique, whatever goals is unachieved by the bottom level policy denoted by G unmet here will be replaced by the goal achieved by the bottom level policy, and then we recompute the reward accordingly with the new goal. We also want to penalize the goals produced by the top level policy if that was not achieved by the bottom level policy, and we use subgoal testing decision where we replace the reward with some kind of penalty, heuristic one. And using this technique, we actually transform an original episode, which is non-stationary, where goals were not always met by the bottom level policy, and we transform into some modified episode where goals are always met by the bottom level policy. And we use a algorithm, a policy gradient algorithm called RDPC to train the top level policy.
So now we'll look at the memoryless bottom level policy. So its mission is to achieve any goal G given by the top level policy within K time steps. And so that's actually a pretty generic Go-based Markov decision process that we can solve using a standard deep reinforcement learning algorithm such as the DDPG. And to counter the sparse reward in that problem, we also use hindsight and experience replay to deal with that. So for experimentation, we created the following 4 domains. They have continuous state observation and action spaces because that's usually the case in robotics applications. They have sparse rewards, can have long horizon, and they all require some form of active information gathering and memorization. So for time constraint, I'm only going to talk about the middle 2, which are the end, heaven, hell, and the end tag domains. So in the end, heaven, hell, as you can see, there's a sort of a T-shaped maze where you have a 8 degree of freedom and robot in the at the bottom. So the AND robot is rewarded, the agent is rewarded when the AND robot enters the green region, and it's penalized when it enters the red region. So we're using sparse reward here. And but the green region and the red region can be on either side. So, and the agent doesn't know that. And the only way for the agent to know the location of the green region is for the AND to enter the blue region. So this problem is challenging because we have to initialize the correct sequence of behaviors that leads to the green region just using the information in that blue region, and that's done through only sparse reward and the deep reinforcement learning algorithm. And in the end tag domain, we have, so sorry for audiences on that side, but we have an AND and an opponent that are initialized in the square region, and we make sure they're not too close together. And so the AND is rewarded whenever it walks close enough to the opponent so that the opponent's inside the green sphere. But this task is also challenging because the opponent can move away from the AND robot, and the AND robot can only see the opponent when the opponent's within the blue region. So look at some learning curves here. So we have the 4 plots corresponding to the 4 domains described on the previous slide. On the x-axis, we have the number of time steps. So that's the number of interactions between the environment and the learning agent. On the y-axis, we have the success rate from 0 to 1. And the first thing we'll talk about is, so our method based on HAC, so-called HILMO, it performs on par or better than all other algorithms on the 4 domains. As we can see in the dark green curve, the green curves, and the other method, HILMO-O, which is very similar to our method, but it's based on a different base algorithm. It performs reasonably well on the door push and 2 boxes, as we can see in the yellow learning curves, but it doesn't learn very well in AND-TAG and heaven hell for reasons we briefly discussed in our paper. And for the flat and non-recurrent soft actor critic, it fails to solve all domains, so that's good to know. And finally, the hierarchical and non-recurrent hierarchical actor critic, which our algorithm is based off of, fails to solve 3 domains, but it learns a little bit, learns an okay policy on this one. So that shows that memory is actually critical for solving these problems. So 2 things to emphasize here. First is that the hierarchical algorithms take much less time to train because when you're merging multiple lower level observations, your top level episodes are essentially shorter. And when you're feeding that into a recurrent neural network, that saves a lot of processing time. And another thing is that for our agent HILMO, as we can see on the left here, it achieves a much better state coverage after 500K steps. That indicates that, as we discussed in our paper, that it learns the lower level policy, a competent lower level policy much faster, which allows the top level policy to explore more effectively. And we want to show briefly the policies learned in the AND domains. So first we have the AND heaven hell. So the AND goes into the blue region following the pink square. So that's like the goal. And in NTAG, the AND sort of goes around trying to remember where it didn't see the opponent, and it sort of tracks down the opponent and try to tag it. And finally, for dirty laundry, the main one is that we need some form of domain knowledge to design the hierarchy. So like what part of the state should belong to the bottom level and top level, and how should we define the goal space for the bottom level? And we encourage ourselves and fellow researchers to think about like how to design a more general purpose hierarchical RL algorithm that we can just like throw at a generic problem to get better performance without much domain knowledge. Yeah, thank you.
All right, wonderful. So now for our second talk, I believe we have Yazid Hassan, who's going to be presenting and getting set up. Sorry, remind me, I'll read out the title. It's the title of the paper is Flock Navigation by Coordinated Shepherds via Reinforcement Learning. Okay, so whenever you're ready, I think you should be able to use the mic, or you can take this one if you want.
All right, thank you. All right, so I'm here to talk to you guys about the work that we did where we used reinforcement learning to teach a group of agents to herd sheep. Now, reinforcement learning is a general algorithm, right? But we all know that in like practice, it's hard to actually simply apply it to a problem. For example, if you're given a Markov decision process, you have your state action, your observations if it's partially observed, your reward structure, your transitions. Then with reinforcement learning, your agent can take actions, and through a feedback loop, you can estimate a policy or a solution. But in practice or in reality, it's not so straightforward. You have to do a lot of tuning. You have to figure out what your reward structure is going to be, what kind of observations are going to work out for you, what features are important. And if you're using a network to estimate, then you have to figure out that as well, your architecture, your algorithm, your input and your output. And generally, whenever you get a new problem, you have to redo all this work. But if you have a problem that's similar to something that's already existing, then you can just reuse your formulation from that problem. The insight that we have is that you can map seemingly different problems to make them similar. So if we map one problem into the domain of another that is already solved and has a solution and a formulation, then you can use that formulation to produce a solution to the new problem. We showcase this by mapping problems that involve active and passive agents interacting, and we specifically look at the shepherding problem. Now, shepherding is a problem where your agents are guiding a group of herd agents, passive herd agents, towards a goal, inspired by real-life sheepdogs. It's a nice example of a complex problem because you have multiple active agents, so you have to consider their coordination, their cooperation, their communication, and there's also interactions between two different dynamics here. And it's a well-studied problem. A lot of solutions are existing where you have a driving point behind it, behind the flock, and you use heuristic or rule-based methods to guide your agents toward that point to push this flock. You also have solutions where you use quadratic programming to find solutions with guarantees. Reinforcement learning itself is also used often, but usually presented with some limitations like discretized environments or discrete actions, or even only dealing with 3 or 2 agents. But it usually gives some robustness to be able to handle, for example, obstacles. Other examples of active and passive agent problems involve oil spill problems, for example, where the passive agents are considered or dealt with as masses, or reach avoid problems where the active agents are supposed to hunt down the passive agents, or vice versa. And one particular problem we're going to be looking at that we're going to be using for the mapping is defender teams. In defender teams, you have a moving payload in an environment where you have a lot of obstacles that are moving around, and you have agents that are protecting it, or defensive agents. Now, this is a prior work of ours, and it has a solution and a formulation that produces robustness and scalability. So if we take a look at the 2 problems next to each other, how do we map from shepherding into the domain of defender teams? Well, we have our multi-agent partially observed Markov decision process at the bottom, and we can look at our state action pairs, and we can see that they're quite similar. They're both holonomic point masses, so they can move everywhere. And then if we look at our active agents in the shepherding problem is the shepherds, and we're mapping that to the defensive agents in the defender team. And we do the same with our passive herds to the passive pedestrians. And then the goal is going to be a special case of the payload that is not moving. Then our observations in the defender teams are 512 LiDAR rays, so they're range limited, and we have 1 channel for each entity type in the environment. So the point positions in the shepherding problem can be translated into LiDAR readings to be able to map into the domain. Now we're going to talk about a few things that are going to be different. The reward structure in the defender teams was meant to keep things out of the payload area. So in the shepherding problem, we're going to design a reward structure that motivates getting things into the goal. And this is the only bit of tuning that you actually need to do for this. And last but not least, the transition dynamics for the defender team problem is meant to simulate pedestrian movement, so it has social forces, whereas the shepherding problem has dynamics that simulate flock animals. So now that we have this mapping going on from between the shepherding and the defender teams, let's look at the formulation that it affords us. We're going to be using an actor-critic network. So it allows us to estimate actions and value, which is good because it's a continuous action and state space. So we kind of need that. And we're also going to be using frame stacking as input to the network. So the previous 3 observations are going to be concatenated and fed in. This allows us to infer velocity and acceleration. And lastly, we're going to be using sharing parameters between the shepherds. So each shepherd is going to have a copy of the network with the copy of the same parameters. During training, this allows for faster training because each of their individual experiences can be used to train the same network, which makes it faster. And during planning, this allows implicit communication between them. So just by seeing or observing each other's positions, they kind of have an idea of what each other is going to do. So they kind of cooperate that way. So we have that formulation and we apply it to here shown here 2 different flock models. On the left-hand side, we have a sheep flock model presented by Strombaum et al. And it represents, and you have each sheep trying to maintain distance to the center of mass. That's the behavior that's going on there. So it's a bit more tight. Where on the right-hand side, it's a Reynolds-Boyd's dynamic. So it's more mimicking birds. And the idea here is that it's maintaining the same heading as the as the rest of the flock. So if we take a look at what they're actually learning, here we have a mapped, the learned heat map value, or the heat map of the learned value. The blue areas representing higher or more preferred areas, and the red areas representing lower, less preferred areas. The big gray blob is the goal region, and the black dots are the active shepherds, and the white dots is the flock. And you can see here, it has a pretty, this is being trained, this is the one that's trained on the sheep agents. And you can see it has a pretty lean strategy. It wants to be behind the flock or next to its other sheep allies. But it generally wants to not be between the flock and the goal. But if we take a look at this map, we can see that when it's trained on the bird dynamics, it's a bit more stringent in strategy. Remember seeing that the flock was very hard to control. So it specifically wants to be very close to the flock and right behind it. And this both shows us that it can, this formulation produces a solution to different flock dynamics without even having to change the formulation or the reward or anything. Just through experience. So we conduct so now that we know that it produces a solution, we're going to see how good the solution is. We're going to conduct a few experiments and compare it to a few baseline methods. The baseline methods chosen here were ones that were applicable to the problem, so continuous state and action, and they drive the agents, the flock from a starting point to the goal and then keeping him there. On the left-hand side, we have a Strombaum-based method, which is representative of all the driving point-based methods. And then in the middle, we have a Pearson method, which is a formation-based one, and it's more concerned with a speed, so it tries to maintain the velocity of the flock. And then on the right-hand side is the deep RL method. And just to point out, for all these experiments coming up, the deep RL method was trained only once. So all the scalability and robustness is like evaluated without retraining. So the first thing we're going to evaluate we're going to look at the scalability of the method by evaluating the time it takes for the flock to get to the goal on the y-axis, and then on the x-axis we have an increasing flock size. And the line in the green is the deep RL method, or the deep RL shepherds. And you can see while it takes takes more than 25% more of the time, more time than the Pearson method to get the flock to the goal, it still takes about only 80% of the time it takes the Strombaum method. And if you take a look at this other plot, we're plotting the average path lengths of the shepherds. So if you're thinking about if it's about efficiency. So if you're thinking about if you have an actual robot with a battery, you can think of it as energy consumption. And you can see here that the deep RL method is taking paths that are 25% the lengths of the other methods. But basically, at the end of the day, we can see that the deep RL solution is scalable, but as the flock size increases. The next few experiments is going to be on robustness. So first thing we're going to see is robustness to observation noise. How this is introduced is we're adding Gaussian noise to the positions of all the entities and then taking the observation on that. But the noise is not actually perturbing the positions of them, just the observations. So on the left-hand side, you have a situation with low noise. So it's behaving kind of similar to the previous examples. But then on the right-hand side, you have something with higher noise. So you can see them shaking all around. If you look at the measured results on the y-axis, again, we're looking at the time it takes for the goal, for the sheep to get to the goal. And then on the x-axis, we have the amount of observation noise, or the size of the standard deviation of that Gaussian noise. And you can see that we still take more time than the Pearson method, but it kind of maintains its performance up until 1.2 standard deviation. And then afterwards, it starts increasing, but still about 30% of the performance that we get from Strombaum. But this tells us that the deep RL solution is pretty robust to observation noise. The next kind of robustness we're going to look at is robustness to changes in dynamics. So we're going to be looking at the flock cohesion. On the left-hand side, we have a flock that's more cohesive. And on the right-hand side, we have a flock that's less cohesive. So it's more spread out. This time around, we're going to be looking at the fraction of the flock that makes it to the goal on the y-axis. And on the x-axis, we're plotting the rho value, which is a parameter of the dynamics. And it's inverse, so the low 0.5 rho is more compact and easier to control, whereas the 4 rho is looser and harder to control. So you can see all three methods perform 90%, 97% or more of the flock and get them to the goal. But as you get to about 3.5 and 4, the Strombaum method drops to about 40%, whereas the other methods maintain their performance. But basically, the deep RL method here is also robust to changes in dynamics. And we've shown that the deep RL method, after all these experiments, is scalable and robust to the dynamics changes and robust to observation noise. So now for some dirty laundry, the realism of the law. I mentioned that we use multi-channel observations, so there's a channel for each entity type. That means, for example, the sheep would occlude other sheep, but they would not occlude the goal from you, so you'd be able to see through them. But other formulations in the related work assume perfect knowledge of position and velocity. So this is kind of an actually kind of a step back. Another thing that we have to address is the shepherding setup that we have is not comprehensive. It doesn't take into consideration obstacles or stray sheep, but we found that by tuning the reward a little bit, you can actually address those things individually. And then the dynamic simulation that we have is, at the end of the day, a simulation. Trying to use this as applicable to the real world is going to have a few speed bumps. It's a simulation, but this is, at the end of the day, some dynamics that we found in the related work that we're applying. And then in the context of the mapping that we introduced, that was meant to be a good, like, you can use this to save you time. We're only showed it on 2 problems in the passive and active agent class. But we actually do have other problems that in mind that this mapping would work for. And we're actually also interested to see if any of you guys can think of any other problems that could be applicable. Another thing is that this mapping is not like a solution to all your problems. There's going to be limitations to this. There has to be some semblance of similarity, even though we're saying like it can be different. It has to have some sort of similarity between them to be able to do this mapping. But at the end of the day, we presented this class of active and passive agents that you can map between to allow you to reuse formulations and solutions, and the solutions themselves prove to be robust and scalable. Thank you very much. That's it.
All right, excellent. Very good. And thank you, Azid, for excellent timekeeping during the talk as well. All right, very good. So for our very last talk of the session, we have, I believe, Wenhao Luo, is that right? Wonderful, who's going to be presenting their paper on sample efficient safe learning for online nonlinear control using control barrier functions.
Right. Thank you for the very nice introduction by Hamid. Hello, everyone. Today I will share some of our work on sample efficient safe learning. And this is a joint work with Wensen from Cornell and Ashish Kapoor from Microsoft Research. So speaking of, sorry. Sorry, I don't know what happened. It's not switching. Okay, try again. Okay, sorry about that. So speaking of the model-based reinforcement learning, and specifically we want to target this domain because it's usually sample efficient and very applicable to the robotics task. So the goal of model-based reinforcement learning is usually by the robot interacting with the environment, we want to build a estimation of the dynamics so that we can perform tasks optimally. So this process involves the robot that keep taking some actions, interact with the environment, and receive some observations about the landing state and the cost about having this particular state, taking this particular action, so that we can gradually use some function approximator to help you build an estimation of the dynamics for the robots. And once you have a relatively good knowledge about the dynamics, then the robot could employ some favorite optimal planner that takes your belief of the dynamics and the reward function so that to come up with a reasonable good policy for the robots to optimize this task. And we have seen many successful examples in robotics domain that having the model-based reinforcement learning to teach a car run on a rough terrain, or to show how to teach a 33 degree of freedom's robotic arm to pick up a spherical object. So, but given this nature of the exploration, as you can see, usually the robot could incur some risky situation where things may not always go right? So when the vehicle is learning how to drive on the rough terrain, it actually could easily crash to the side that could lead to catastrophic consequences. So in this case, what we need is some model-based approach that guarantees safety for the robotic system, right? So talking about safe critical control, we usually know that usually requires some knowledge about the desired safety constraint, and then the perfect model or some noisy model of the robot dynamic system, so that you know how to constrain the action of the robot so that the robot could remain in a relatively safe set, right? But as we mentioned, usually, in order to have a high quality of safety critical control, we usually require either perfect knowledge about dynamics or some conservative estimate of the dynamics, which could be overly conservative if you want the robots to proceed with some task. So in this case, we really think about what if we do not know the dynamics of the robot? How we're able to use data-driven method to help robot efficiently learn the dynamics and perform its task. So this leads to our objective of this work, which we focus on 3 domains in the model-based reinforcement learning, which first of all is the sample efficiency, second is the safety, and third is also the control performance, right? So initially we want the robots to guarantee safety, not only when testing, but also when exploring the environment. And second, we want the robots to be efficient, because the robot can just sit there and do nothing, but it will not help the robots learn anything new about the environment. And with these 2 points, we also don't want the robots to exhaustively search in the space just in order to learn its dynamics. So what we want is the robots doing the learning, they still want to achieve some good performance, right? So with this objective in mind, let's delve into a little bit of details about the concept, the specific question we're trying to solve. So given system dynamics, and we model it by first of all, the nominal dynamics represent your current knowledge about dynamics of the robots, and then plus a unmodeled dynamics. So the unmodeled dynamics here could be model uncertainty or some mismatch of model due to the imperfect knowledge about physical parameters. And we assume the system suffer from addictive Gaussian noise to represent some stochastic. So with that, in this work, we assume that this unmodeled system dynamics could be represented by a linear mapping over a known feature mapping space. So you can consider this phi as a high dimensional embedding representing a known feature mapping from the state and action space towards a high dimensional space of the embedding space. So with that, we are able to represent a wide class of nonlinear system, including autonomous, including the cars or manipulators or quadrotors. So with this assumption, basically how to represent the dynamics of the robot boils down to how to derive or learn this linear mapping of W as a weighting matrix so that we can accurately capture the data of this model dynamics. Right? So when we don't think about the learning for a control problem, if you are given a h time steps, so what you want is to minimize the objective function in this h time steps, subject to, first of all, the safety constraints, representing you want the state of the robot always stay in a particular set. And the second, you want the robots to satisfy these ground truth dynamics. You can easily basically solve this problem by any model predictive controller. But the challenging part is when you do not know the dynamics of D, meaning when you do not know the linear mapping W here, then the robots could run into risky situation or even not perform the task optimally, right? So in this case, what we want here is basically efficiently learned weighting matrix W star so that we can safely optimize the control performance. So with that, we follow the evaluation matrix by the learning community, which is basically a safe learning objective focusing on regret minimization plus safety. So for this one, we're assuming we have a capital T episodes of training episodes. And what we want is to minimize the regrets, representing the difference between all the costs that the robots receive during learning in this total T episodes and the ground truth minimal or optimal performance of the robot if assuming the robot knows the ground truth dynamics. So desirably, you want the robots to achieve some bounded regret so that if you're assuming the T episodes goes to infinity, the robot could approximate to the optimal control performance as if you know the dynamics of the robot. Right? And of course, you want the robots to subject to safety constraints at all times. So the key ingredients that enable us to solve this problem is, first of all, that we use the control barrier function in a stochastic setting to enforce the safety with high probability under iteratively learned model uncertainty. And second, we want to integrate a optimism-based strategic exploring algorithm that help the robots to efficiently guide towards this exploration process. Right. So for many of you may already be familiar about safety through control barrier function, which is a very useful tools. So the main high-level idea of the control barrier function is assuming you want the robots to stay in some particular safe set and whose zero super level set representing by the function h of x. So what you want is to integrate in the dynamics of the robot so that you can find a particular constraints over your controller so that the resulting behavior of your safe function will not decay as fast as a comparison function here shown in red. So in this case, you're able to make sure the robot state h is larger or equal to 0, implying the robot will remain safe at all times. So in this work, we use a stochastic extension for Gaussian noise, right? Because there's due to the stochastic in the robot dynamics, we want to be a little bit more conservative so that the robot could remain a safer condition. So in this case, you can see this little capital delta term representing some conservative estimation of this noise. And with that, we are able to still obtain a set of deterministic control constraints so that to enforce the safety for the robot. So now let's look at a brief overview of the optimism-based safe learning for control. So assuming at any training episode T, we have an aggregated data set which representing the state action pair and the landing state of the robot. So with this information, we can easily use the linear regression or ridge regression to calculate the current best estimation of this unknown linear mapping weighting matrix WT, as well as its covariance matrix sigma T. So what we do here is that we can represent this current belief of the ground truth linear mapping in this ellipsoid. And what we want to focus is not what we are confident about, it's about what we are uncertain about. So if we're assuming this linear mapping, this phi is in two-dimensional space, so the longer principal axis representing we have more data already collected along this dimension, and the shorter one representing less data. So in this case, when we prepare for the exploration, we want to basically take rotate this confidence ellipsoid by 90 degrees so that we can focus more on the principal axis representing dimension where we have less knowledge about, right? So in this case, we employ the Thomson sampling so that the robot could, at every round, the robot will pick up, hopefully, the dynamics represented by the linear mapping that is having less knowledge of the current ellipsoid. So once we have this sampled knowledge of the linear mapping, we can then use that as your current belief of your dynamics, and then use your favorite MPC solver to solve these particular control actions in order to optimize a objective function. And of course, we will use this stochastic setting of the control barrier function to guarantee safety with high probability during the process. And once we have these control actions policies, then we can execute it and then collect a trajectory represented by a set of state action and the landing states. And then we can aggregate the data set and prepare for the next training episodes. So let's look at an example of using that algorithm. Let's consider an invented pendulum problem where you want to stabilize the pendulum upright position. And here we introduce a safety constraint representing the condition that you don't want this inverted pendulum to hit this blue stick. So this may not seem as interesting as a running car, but they share very similar dynamics of the dynamics equations. So in this case, if we run a naive model-based reinforcement learning with the safe control, you can see because of this incorrect dynamics model, the robot or the pendulum could easily collide with this blue stick, implying the safety constraints being violated. And if we use our method, as we can see, first of all, we start with some pre-collected data, and then we introduce, and we use an optimism-based sampling method to get the linear mapping And at the episode 0, because of the less knowledge about the robots, the pendulum is very suffering from this local minimum and not swinging up. But as the robot's collecting more data along its way, let's see episode 30, the robot is kind of like making progress towards the optimal position while always respecting the safe constraints. And when at episode 50, the robot is successful in stabilizing this pendulum without any violation of these constraints. So here we have another examples on the simple case of mobile robot navigation, where we have the robot with the initial dynamics that without knowing the actual wind field in the background, and the robots want to move in this environment, collect data, learn the wind field, and try to avoid collision with the obstacles. So in this case, as we can see on the left-hand side is our method, and the right side is a safe exploitation method. And after 10 training episodes, our method during testing is able to take advantage of this wind field downstairs that the robot have no idea beforehand. While compared to the right-hand side, the robot was stuck in some local minimum because of the lack of exploration in the environment. And we have more quantitative results in the paper. So in general, the conclusion is that in this work, we're basically focusing on using the optimism in face of uncertainty to encourage sample-efficient reinforcement learning. And by combining with control barrier function, we are able to maintain safety during learning and testing. And in the paper, we also follow the proof of the bounded regret analysis, proving the theoretical results of the sample efficiency. So regarding the future work, as you can see, the robotic example is kind of like simple. It's inverted pendulum and mobile robots simulated in MATLAB. So in the future, we're interested in how to implement this method for real-world robotic experiments on more complex and high-dimensional system. And for the limitations, we know that in our application, there's a very strict assumption that we should remain feasibility of the control barrier function, meaning that you cannot start the robot at the boundary of the safety region, that you may probably have no safe actions by that time. And the second is that we require a reasonably good initial model from the pre-collected data so that you have a roughly good estimate about the things that you don't know. And with that, I'd like to stop here. Thank you.
All right, wonderful. Don't go too far. So if I can now ask the speakers from all 3 papers to come and either stand around or sit at the front, as per your preference, we can start the question and answer session. All right, very good. So it seems like we already have some volunteers from the audience. So I suppose I'm in charge of calling out. Why don't you go ahead, and we'll try to make sure that we keep it somewhat balanced between the talks if possible.
Hi, thanks for the great talks. So I have a question for the last presenter. So I didn't quite catch the form of the CBF. I wasn't sure if the CBF is actually a function of your current estimate of W or if it's independent of that.
So your question is about whether the current sample W is part of the control barrier function.
Wait a second. Let's see if we can get a mic that. Just a mic that we can pass around to make sure that folks can, yeah.
So, sorry, I'm asking that whether the sample dynamics is part of the control barrier function constraints.
Right. So basically, you're learning this D function, which depends on W, right? That is trying to correct for the error in your nominal dynamics. It seems like in order to be safe, you want your CBF to have some sort of a bound on how far off from the nominal dynamics you are. Is that part of it? Because I didn't catch
Oh,
that.
yes. Sorry, we didn't show that explicitly in the presentation. So yes, the learned sample dynamics is always part of the current control barrier function that you use, and that representing that how good that your knowledge are based on all the data you have seen from the history trajectories. Yeah, so.
Okay, and just a small follow-up question. When you sample W from this ball, when you're doing the Thomson sampling, is that really what gives you the bound on the magnitude of the disturbance between your learned and your true dynamics? Because the ball is bounded, or does that bound come from somewhere else?
Oh, yes, the ball is bounded. So in the paper, we mentioned that initially we're assuming you have a pre-collected data set representing initial bound of the ball, so that you just do the Thomson sampling inside this ball to remain safe and high probability of sampling these ground truth dynamics.
Got it. All right, thanks.
Yeah, thank you.
Thank you. Sorry, it's also thanks for the presentation. It's also for the question for the last speaker. So it's a very interesting approach. I was wondering actually two questions. The first one is like, we didn't really see the formal guarantees of the regret or the sample capacity. So I was wondering, because you are using, I'm wondering how did you implement this optimism oracle? You are using Thomson sampling, and I guess the guarantee should be Bayes regret, but the definition you had seems to be like the high probability regret we have seen. So it seems there's a mismatch. Maybe I misunderstood.
Right. Yeah, good question. So we are not following the Bayesian settings in this case. We're just assuming that the regret is compared with the ground truth dynamics, if you know that and how optimal you could achieve this. So basically we use the Thomson sampling, and also we are assuming you have an optimal planning oracle that you can call, so that, for example, if the Thomson sampling sample the ground truth dynamics, then by using this optimal planning oracle, you are able to achieve the optimal performance. And the optimal planning oracle, what we're using is the model predictive path integral method.
I see. So I guess that's the missing part. I was wondering what's the optimism planning oracle you're using.
Right.
So second quick question is more about the comparator. So from my understanding, the CBF is like a sufficient condition to ensure like safety, but the V star is a comparator compared to the actual safe optimal policy, or it's the optimal policy that satisfies the CBF. In the regret, you have a comparator like V star.
Right. So you mean the regret between the cost and the ground truth cost?
Yeah, the ground truth is that the optimal ground truth is the one that optimal the value and also satisfy the
yes, also satisfy the
safety constraint or satisfy the CBF condition. I think they are slightly different.
Yeah, that's a very good question. So theoretically, we're assuming that is satisfy the safety constraints, but in the implementation, we use the CBF-based approach to approximate that. But you are right, there is a gap. For example, using CBF-based approach can maintain safety, but not all the safety condition could be represented by the CBF constraints.
Got it. Thank you so much.
Thank you.
Another question for the last speaker. So I'm curious how you kind of designed the feature mapping, because that seems like a kind of a strong assumption to kind of know a set of kind of predetermined features that are going to span your true dynamics. And I guess a follow-up question on that is like, how does the number of unknown basis functions factor into the kind of effective sample efficiency of your method, as well as is it possible that if you have too uninformed of a set of basis functions that you actually just can't do anything. You can't ever kind of do anything with the existing CBF that you have.
Yes, that's a very good question. So for the feature mapping, then of course we are assuming that they are representative enough to represent your dynamics. Like in our case, we use the random Fourier features in 200 dimensions of that, and you can also use the Gaussian kernels and things like that. And what we do assume is that this can be represented about your ground truth dynamics. And regarding the regret analysis, the regret will be dependent on the dimension of the kernel that you choose. So basically the dimensions are there, but we don't explicitly depend the regret over the dimension of your state space or the action space.
I guess just a quick follow-up. So I guess, is there a way that, like say you have like 200 features, but it turns out that only like 10 of them are actually really relevant. Is there a way that you can detect online like which features are relevant to potentially improve like the analysis?
Yeah, so actually can be captured by the confidence score that we mentioned, right? So for example, if you choose 100 data point and then many of them are following a very narrow region over this confidence score, then that means basically that kind of part may not be that relevant to others. Yeah, but we just use the standardized one and we fix the dimension. We don't do the PCA analysis and the reduced dimension, things like that.
Cool, thank you.
Thank you.
I have a question for Yazid on your paper. So on your scalability slide, it showed that your deep RL method outperformed the other methods in the shepherd path length, regardless of the size of the flock. But in your paper, you say the reward structure consisted of a penalty for obstacles colliding and breaching the payload region and a reward for the payload reaching that goal. Do you have any insight as to why the path length was that much better than the other algorithms?
So you're asking about the algorithm for the shepherding, the solution for the shepherding having 25% of the other solutions, whereas, and relating that to the reward structure of the shepherding or the defending problem?
The shepherding problem.
Okay, the shepherding, yeah, okay. So what we see that is in a lot of the algorithms that we have, the baseline methods that we're comparing against, a lot of them do like continuous actions right after you get when you get the flock to the goal to try to keep it there. Whereas our algorithm, the deep RL solution is like finding a solution where it like spreads evenly around it to maintain it there, so it doesn't move as much. And that's coming from the just keeping things in the goal region, because it's per like time frame in the episode. So if something does actually come out of the goal region after it entered, it notices that like it sees that it's actually getting less reward. So it is like that's probably directly contributing to that, but it's reinforcement learning. You can only assume. No problem. Thank you for the question. That was a good one.
A question to the second speaker. So I really like your work about mapping from one problem to another similar problem. So I'm just curious, like, do you have any formal metric about the similarity between two RL problem?
No, not yet, but we're looking into that. We're looking into how to like figure out the similarity or the degree of similarity that you can get away with something like this, how far you can push it. If you can get something like degree of difference, like some static number or something, maybe in relation to the Markov decision process or the formulation itself. But yeah, right as of now, no, but that's the kind of thing we're looking into and seeing if it makes it easier for us to specify if something can be mapped or not. But yeah, thanks. It's a good idea.
Thank you. So that's a question for the first talk. Thank you very much for the great work. So you introduced the concept of MobDBs as a formulation that could be applicable to various problems in robotics. Could you talk a bit more about the broader relevance to real-world domains? What other tasks do you envision we could tackle, we could describe with this formalism?
Yeah, I'm thinking about like in the paper, we kind of have the example. I mean, it should be applicable widely to the robotic world. That is the gripper, right? So in the gripper, the pulse of the gripper can be considered to be fully observable because it can kind of measure quite accurately using a sensor of the grippers. But for instance, the object that for instance, the gripper wants to grab something that is unknown, then that one has a uncertainty kind of much bigger than the pulses of the gripper. And that is like an obvious example of applying our method to the gripper. And like gripper is used everywhere, so.
Got it. And another question I had was you talked about how domain knowledge is basically required to break the problem into high and low level and bottom level. Could you talk to us about how would one go about doing that, or if you have any thoughts about how to make this process smoother? Was that very challenging to get it right? What are your thoughts about that?
Yeah, I mean, that limit is kind of the limit of the hierarchical method that we apply our method on. So if you remember, we apply into there are two ways like the hierarchical isokinetic HAC and the hero algorithm. So they kind of require you to have such domain knowledge, to break into like what should go with the bottom levels, what should go with the top level. But our method can be, it doesn't need to have to be that way, because the bottom level actually can use the same observation from the top levels, like the raw observation, and it should be doing okay in that case. So I don't think that that is like a big kind of limit to our method.
All right, great. So I think we're essentially at time. Unless we have any burning questions at the very last second, I think we can end the technical part of the session here, and I'll pass it on to Dorsa.
All right. Okay, so that concludes the first day of WAFR. Thank you all speakers, respondents, chairs for contributing. So we have an hour and a half, so we can just go to the hotel, hang out, do emails, whatever we're doing in the next hour and a half, or we can just hang out in the bar at the hotel. And then at 6 p.m., we are going to have a reception. The reception is not going to be in this building. It is going to be in a different building. That is the computer science building, the Brandon IRIP building, which is right in front of the hotel. So if you're staying at the hotel, then it's going to be right in front of it at 6 p.m. All right, we'll see you guys there. Tomorrow we'll start at 8:30.